Good afternoon from Asian Development Bank Institute, Tokyo, and good morning to all of you who are in other time zone. I'd like to welcome you all to this virtual conference on water resource management for achieving food security in Asia under climate change. So this is the second day of our conference. We had very interesting presentations and discussions on the first day. There were many things that was pointed out. One of the important thing that was pointed out by some of the studies, but many could not capture that, is about the issue of sustainability of groundwater and water resources. So I hope we'll be able to hear more about sustainability issues in today's presentations and discussions, which is very crucial. So I'd like to introduce the chair of the day. So today, Dr. Professor Changfeng Liu will be chairing today's session. Professor Changfeng Liu holds PhD in Agriculture and Resource Economics from the University of California, Davis in 2008, holds the Boya Professorship at Peking University, and is a Senior Research Fellow at the China Center for Agricultural Policy. She also serves as the Associate Dean at the Schools of Advanced Agricultural Science. For more than 20 years, she has worked on development economics and applied microeconometrics. Her work is highly empirical, drawing on large number of data sets that she and her co-authoring team have collected in rural China. Currently, her research has its full focus on human capital, including issue of rural education, health and nutrition, and rural transformations. With her co-author, Dr. Liu has published more than 120 papers in peer-reviewed journals, both domestically and internationally, including Journal of Development Economics, Journal of Labor Economics. In recognition of her work, Dr. Liu received the China National Science Fund for Distinguished Young Scientists in 2019, one of the highest academic honor that can be bestowed on a young scholar in China. She serves as the chair of China sections of Agriculture and Applied Economic Associations during 2019 and 2021. Thank you so much, Dr. Changfeng, for joining us and for willing to chair the sessions. I'd like to give the floor to you.
Okay, good afternoon, everyone. Thank you very much, Dr. Rahat, for the kind introduction. It's such a great honor and a pleasure to be here to serve as the moderator or the chair of this session. So this afternoon, we are going to have 5 very interesting presentations. So without further ado, let's invite the first presenter. I think, the first presentation will be on the contribution of agricultural development interventions to the climate resilience of semi-arid farming systems in India, presented by Dr. Arjuna Srinidhi, PhD research scholar, Water Systems and Global Change Group, Wageningen University and Research, India. So Arjuna, the floor is yours.
Thank you, Dr. Liu, for this, for your warm words of welcome, and Dr. Rahut for the introduction to the day. I'm really excited to be here, and thank you very much for the opportunity to present the work by my colleagues from my organization and Wageningen University. So my name is Arjuna Srinidhi, and I'm associated with Wageningen as a PhD candidate, but also with an NGO in India called Watershed Organization Trust, based in Pune. The work I'm presenting today is part of my PhD thesis on climate resilient development pathways for semi-arid farming systems in India. But this current paper focuses on assessing the contribution of various agricultural development interventions to the climate resilience of these farming systems. Let me begin with a bit of context. This picture shows the typical landscape that you see in the semi-arid parts of Maharashtra and India. And dryland regions consisting of arid, semi-arid, and subhumid areas cover almost 55% of the areal extent in India. The semi-arid regions in particular are dynamic and easily influenced by changes in climate, availability of water, farming practices, that are in turn influenced by markets and policies. So over 85% of the farming community here also consists of small and marginal farmers, and this contributes to the underlying vulnerability of this region to climate change. We see that there are several emerging projects with interventions aimed at improving the resilience of these farming systems, but we argue that many of these have a narrow understanding of resilience, and they provide sometimes very generic suggestions that are not context specific. And so we see that there is a need for clearer, evidence-based understanding of how interventions are contributing to the climate resilience of farming systems. And this forms the core objective of this paper. We aim to address this objective in 2 steps. One is by assessing the climate resilience of 2 selected farming systems or case studies, and is in the second step by applying a pathways lens to assess the cumulative impact of the sequence of interventions in each farming system and drawing insights on the contribution of specific interventions to its climate resilience. So here is a brief outline of the rest of this presentation. I will elaborate to begin with on the conceptual framework and the methodology. I will include details of the case study, the data collection, the data analysis. We will then discuss the findings from each of these case studies. And I will then provide a synthesis of the key findings, which in our main paper is also elaborated into 5 policy recommendations, and finally a few concluding points. So for our first step of assessing the climate resilience, we use a 6-part framework, which is called as the CRISI framework. The full details of this framework is part of how this framework was developed and tested as part of another paper. The framework essentially distinguishes between 2 kinds of resilience, resilience to specific climate stresses like droughts or rising temperatures, and also resilience to unknown risks that are captured by a set of general resilience attributes. For assessing the specific resilience, we work our way through the parts of the CRISI framework that capture the system description, the challenges, the performance of its system functions, and also the insights about how the system functions are changing over time gives us an understanding of the system's resilience capacities. These include anticipation, robustness, adaptability, and transformability. These 4 capacities and the general resilience attributes in part 5 allow for quite a holistic understanding of the resilience of the system. And to improve the accuracy of the assessment, and we also have a part 6, which includes a step of reflection with the stakeholders and the community involved in this in the study. Now, together, these 6 parts contribute to the first step of the assessment, the climate resilience assessment. But since farming systems are also subject to different interventions over time, we apply a pathways lens that helps us understand the cumulative effect of all the interventions and the contribution of each intervention to a specific function or an attribute. For this, we plot the performance of the system function and attributes over time, and we also do a content analysis of the notes from all our stakeholder discussions and map each intervention to a specific function or an attribute that it contributed to. I will discuss this part in a little more detail when I come around to the results. Here I show the location of the 2 case studies that we are dealing with in this study. Both of them are located in the semi-arid parts of Maharashtra in India. CS1, case study 1, was aimed at improving the agriculture productivity and irrigation infrastructure. A lot of the interventions focused on these 2 aspects, while in CS2, the interventions targeted building of adaptive capacities in addition to improving agriculture productivity. The interventions in CS1 are also part of typical large government programs like the Integrated Watershed Management Program and the State Rural Livelihoods Mission, the implementation of which are quite standard and follow generic guidelines across the rain-fed regions in India. The interventions in CS2, however, had an NGO involved in various projects since 2008, and therefore this case study has a much more customized approach for planning, implementation, monitoring, and evaluation of its activities. So you see that the selection of the case studies was quite deliberate to have an idea about the different pathways and interventions in and how they contribute to the resilience. This is, and here you see a detailed timeline of the activities that were there in each case study. We selected a 15-year time span for the assessment. The reason for this was that stakeholders felt that interventions prior to 2007 did not contribute much to its current resilience. Both case studies you see had watershed development, the typical watershed development interventions like soil and water conservation to begin with at the start of this timeline. In case study 1, this was followed up with interventions that had a focus on improving the irrigation infrastructure through pipes, solar pumps, and in addition to some focus on alternate livelihoods and microfinance in later years. In CS2, the impact evaluation of the earlier watershed development work was followed up with interventions like climate resilient agriculture, water stewardship, food and nutrition security, and also getting farmers involved in a farmer producer organization, which is another relatively recent intervention here. In terms of our data collection, we followed essentially a participatory rural appraisal process with stakeholders in 2 kinds of settings. One was a mixed multi-stakeholder group where common issues like the purpose and views about the system were discussed. These meetings, are often tend to be dominated by the larger and the more influential farmers. So we also had a few specific focus group discussions with marginalized sections like women, the landless, any marginalized castes, which also tend to be the smaller farmers, and youth to get their perspectives about the system and its resilience also. And together, the PRA exercises over here covered the first step of our research in terms of assessing the climate resilience using the CRISI framework, and also provide inputs for the second step in terms of application of the pathways lens. The data analysis for step 1, the climate resilience assessment, was relatively straightforward. The qualitative data from the village meetings and the focus group discussions contribute to parts 1 to 4 and 6 of the CRISI framework. For parts 3 and 5, this involves scoring of the functions and resilience attributes. This was done on a relative scale of 1 to 5, where 1 was assigned to the lowest possible form of the attribute that could be imagined by the participants, and 5 for the highest. Taken together, this qualitative and the quantitative data gives the overall picture of the climate resilience of the system. The analysis of the second part, the application of the pathways lens, was a little more complex. We manually coded the transcribed notes using Excel with a mix of deductive and inductive codes. For example, if somebody spoke about watershed development helping better groundwater recharge through water trenches, this was given the code of the intervention, and another code for the function of agriculture productivity or health of ecosystem it contributed to, and say an attribute of ecological self-regulation. So this was how the coding was done, and we used the coded file to map the codes of the stakeholders from the intervention to the function or attribute that it contributes to. Coming to the findings from the case studies, you see here some of the results from the climate resilience assessment of CS1. In the interest of time, I'll focus more on the quantitative part, that is the performance of the system functions and attributes. But a couple of qualitative points worth mentioning to begin with are that CS1, the case study 1, always had better access to water from a nearby check dam, and so is endowed with a nearly perennial access to water. Whereas CS2 does not have such an abundant access to water and also had poorer soil health to begin with. These differences in access to natural resources also are reflected in the cropping pattern of the 2 villages. CS1 is characterized by more cash crops like cotton, sugarcane, soybean, horticulture, while CS2 was characterized by other crops like cotton, maize, wheat, sugarcane, pearl millet. There's also an active dairy in CS2 that contributes to a more mixed crop livestock farming system. But coming back to the quantitative performance of CS1, what you see here is a drop in the performance of some of its functions in 2012 when there was a drought. but overall, driven by the agricultural development interventions that included the focus on irrigation infrastructure and solar pumps, you see agriculture productivity has gone up, the profitability has also gone up. However, this seems to be coming at a bit of a cost due to the intensive agriculture being practiced here and the focus on cash crops and chemical fertilizers. Farmers spoke about declining soil health and increasing in vulnerability to water shortages, health risks from the chemicals. So these you see are reflected in dropping of the scores for the health of the ecosystem and the ecological self-regulation. And you also see that the interventions in this case study did not do much to improve the social regulation or the governance systems that could support transformation. In this chart, I basically show the scores of the functions and the attributes, but as an aggregate, along with the timeline of the interventions that happened in this case study. The overall story that you see here emerging is that there hasn't been much of a change in the overall resilience of the system, the specific or the general attributes. And this is because the improvements that were driven by the intensification in agriculture productivity has sort of somewhat been negated by the reduction in the health of the ecosystem and attributes related to equity and social organization. There has been an attempt at livelihood diversification in recent years, but this has benefited a very few households to date as per our interactions. Coming to the case study 2, we find that without the same access to water and good soil resources as CS1, this one had a much lower scores of system functions to begin with. But given this lower starting point, we see a rapid rise in both of its system functions and attributes with the start of the watershed development work. The scores in 2012 in some of the cases would have been even higher, however, if not for the drought year that was experienced. But in general, overall, you see that driven by the interventions that focus on better management of its natural resources, the water stewardship, the climate resilient agriculture, all its resilience attributes, and including building of human capacities shows an upward trend over the years. And here you will see how these interventions related to building of capacities for water stewardship, for food and nutrition security and all, and how these interventions in later years has contributed to the improvement of the general resilience attributes and the overall improvement of the resilience of the system. And these interventions, especially because they had a very strong focus on capacity building, they also led to an improvement in functional diversity in the system and agriculture productivity that was not just based on intensification, but also on more crop rotation, intercropping, a mixed crop livestock system, and a better management of its water resources. In addition, we see some of the interventions had a focus on contribution to the governance systems that improve transformation. The village water management teams that were part of the water stewardship initiative, and also the farmer producer organization contribute to this attribute by providing a platform for discussing challenges and novel solutions. With this, I come to an overall insights from both the case studies and a synthesis of the key results. What we find is that in both the case studies, the initial watershed development work led to an intensification of agriculture and changing cropping patterns that also led to a dropping in water table and declining soil health. From CS2, we find that the climate resilient agriculture, water stewardship, and food and nutrition security built capacities and responded to the above issue. The FPO in CS2 responds to the need for introducing economies of scale and improving profitability, especially for the smallholder farmers in this region, although the FPOs also have some challenges with regard to sustainability. We see a few non-farm livelihoods coming up in CS1 in particular, but access to credit and capacity building for entrepreneur skills remains a challenge. And a final finding for us from both the case studies was that despite the presence of smartphones and some apps from climate service providers, the penetration of such technology and information needs to improve, especially for short and long-term climate forecasts and agriculture advisories based on these forecasts. To conclude, I have three final points that the agriculture interventions in semi-arid areas have shown a general bias towards agriculture productivity and neglect the improvement of some of the other system functions and its general resilience attributes. But we find that a broad range of interventions addressing multiple challenges, along with a focus on monitoring, evaluation, learning, and adaptive decision-making are important for building the climate resilience of semi-arid farming systems in India. And we find that the application of the pathways lens is very useful in assessing multiple risks and the cumulative effect of a wide range of interventions for a time period of like 15 years. With that, I would like to end. Thanks to my colleagues, my co-authors, and the wonderful people of the two villages. And that's a picture of my colleague and me doing the fieldwork and the case studies. Thanks.
Thank you very much, Arjuna. That's really interesting. And now let's invite the discussant, Dr. Subhasis Bera, Associate Professor from International School of Business and Media, India. So, Dr. Bera, the floor is yours.
Thank you very much.
Thank you.
Good afternoon, everybody. Let me share my screen. Well, it was a nice presentation, and I don't think I will have many things to talk about. But the first thing is that whatever the things I will talk about, it's basically to take the discussion further, rather than finding out the limitations of the study. So before I start, I would like to highlight what is the main focus of the study. The research is based on the retrospectively assessing the contributions of the agricultural development, and for that, the study selected the two farming system to find out whether intervention aimed at improving agricultural productivity and in the irrigation. And the second one is talking about the adaptive capabilities. And to do that, we understand we need to talk about the climate resilience, and we need to talk about the multiple hazards, and we also need to talk about the underlying socioeconomic vulnerabilities. And that's why any study related to climate resilience is very difficult. And to do that, this study have taken the two steps. One is the CRI-SI framework, and the second one is the pathway lenses. And it was nicely explained by the author. And the time period was taken 15 years, which is pretty long to understand how the movement and the development process is working. Now, the first major finding of the study is that there are many findings, but then I'm just highlighting one point in which we'd like to discuss further. No single strategy can effectively build climate resilience. The second one is agricultural development pathways in semi-arid areas have met with much success. The third one, the CS2, means that one particular village carry out a water budgeting exercise and undertake crop planning based on the actual rainfall for the given year. And the fourth one is the lesser focus on the non-farm livelihood. The first point that my comment is that the two villages chosen for this analysis are dissimilar. And one village is having an easy access to the water, and where the other one is having a shortage of water. Now, when we choose two distinct villages, it has an advantage and as well as a disadvantage. The advantage is that we can analyze the multiple dimensions with an assumption that each village will act similarly in the similar situation. However, the disadvantage we are having that the two distinct villages naturally will show the different reaction due to the difference in the dwelling environment, even when the same strategies are applied. Having a similar platform or the environment as a criteria for comparison will be missing here. So what exactly we are trying to do here? I mean, we need to understand that whether we are trying to figure it out that how the different villages are behaving differently, or whether these interventions are effectively working in everywhere. The second thing that I would like to point out that since there is an access to water, individual initiatives or activities are far more prominent in the CS1, indicating that the lesser importance in the community development. However, agricultural development largely depends on the community rather than the individual efforts. And CS1 clearly access to the resources, initiative, and for the community development are not holding hand in hand. Whereas CS2, where resource constant is there, the individuals or the households will focus more on the community development. This is a more of a reaction for the survival. Now, another point that I would like to make here, the distributions of water may require energy resources, although the author have mentioned that solar pump, but not adequate information regarding the availability of energy resources is there. Because when you talk about the distributions of water, I need to know how the water is distributed, all the lands, all the small pieces of land. And study also highlights that landless, marginalized farmers are not given enough importance in the water distribution. Now, I think the landless is, when I'm talking about landless, marginalized farmer, I also have to, the author also needs to mention that the farmer is actually farming, taking a land from a landowner on a crop sharing basis or something like that. Otherwise, a landless farmer doesn't need water for agriculture here. And second thing that I would like to talk about is the score. That the score provided by the different individuals may not have the same standard, especially they belong to the different environment. Hence, the comparison may not be accurate. And again, providing scores for the past years is also subjective and it relies on the present status. So when we are asking them, or when we are asking them to rank, and we have to be very careful about that. The second point that I would like to make here is that climate resilience requires awareness, which in turn helps anticipate, to prepare and address a future problem. Author did mention the anticipation, but inclusion of awareness and analysis would have been enhanced the impact of the study. And again, the awareness is a function of available information, although the study mentioned the technology use and the information sharing, but there is not much discussions about the information sharing among the people. And the author also mentioned about the smartphone use, but nowadays in India, in many states, the information regarding the climate or information regarding the price of the crop are sent through the SMS. So for those kinds of informations, one need not to have the smartphone. Even a simple normal mobile phone will do. And every individual looks for an incentive to participate. So incentive motive is another aspect can be looked at, although study talks about the FPO, which considers the profitability. There is not much other initiative or emphasis on the study. And here, especially when we are talking about the development, we also need to consider both the things together. One is proactive and the reactive strategies. So here, most of the point or points were made on the reactive strategies. There was no mentions of the proactive strategies. I think that can also be added in here. And few other points, it's small, but an author also have mentioned that the soil of CS1 is better than the CS2. But as for the table, we see there is no soil testing after the 2007. And so whether the soil is better or better, that depends on the perceptions of the farmer only. Yeah. So I think even if we put a little bit of statistics here or for any crop, then I can one can compare whether the soil quality is degrading or not. And then author also mentioned that human capital building for agriculture or for non-farm activities. And he mentioned the human capital building, but it didn't distinguish whether it is for agriculture or non-farm activities. That mention would have been better. And governance arrangements that's in the support transformations. What kind of transformations we are talking about? And another point is also the study touch upon the topic related to the recruitment technology, as I have already mentioned, but there was no information about how many households are already using a mobile phone. And if large proportions of the populations of that particular village is using a mobile phone, then probably that information can be shared, because information sharing is very important, especially when we are trying to build up the resilience. And there is no mention on how the intervention is creating stress on the health of the ecosystem. In the page 6 there, where when the government come up with policy, especially for the water and the management things, they definitely look at the health of the ecosystem. But it is not the intervention that is creating a stress of the health of the ecosystem. Probably other activities that is creating health stress on the health of the ecosystem. I think a little discussions, a few lines would have been better here. Another point is, as I already have mentioned, how agriculture intervention help landless household, unless they are farming on a borrowed land on a crop sharing basis. Again, a few lines would have been better here. And when we deal with another important thing is that the author has categorically mentioned that there should, it is a multidimensional aspect, and no single strategy can overcome this problem. This is very obvious. So any intervention is there, it has to be biased, because it is always targeted to a specific problem. So therefore, what we need to do that when government come up with the strategy, they come up with the multiple strategies, and whether that a synergy effect is there, it is positive or negative, that needs to look at. And that's my point. And another last point that I would like to make, that the model is based on the CRI-SI framework and developed by Srinidhi. That reference, what I see is that it was written only the working paper. So I searched at the Google and I couldn't find that paper. So if a proper referencing is there, then it would have been easy for me to look at the things. That's it. Thank you.
Okay. Thank you very much, Dr. Vera, for those insightful and constructive comments. I'm sure they are appreciated by the presenter and his co-authors. Dr. Arjuna, do you want to respond quickly, just in 1 or 2 sentences to Dr. Vera's comments? Thank you.
Yeah, sure. No, I'm very grateful to Dr. Vera for taking the time and the interest in for a detailed assessment of the paper and for sharing his valuable feedback. Yes, I think the overall challenge is that resilience itself is like quite an overarching term. There are so many dimensions. And when you look at farming systems, again, there is agriculture, non-agriculture, there are different kind of stakeholders, actors. So it becomes quite complex, but nevertheless, that is the scope of the paper, so it has to address each of these things adequately. Yes, I've made a note of many of the points, and I think many of these can be addressed with some more clarifications, explanation. The soil testing, the access to water, access to smartphones, data around it can definitely help. Yes, I think just one point that I wanted to highlight is that especially the comment about the choice of the 2 case studies being dissimilar is a very valid one. We were also very conscious of it. And in this instance, we felt that it gives us the scope for a wider range of activities and dimensions of the human behavior and an intervention that can be explored. But certainly maybe with more case studies, it can be even stronger or can make the policy recommendations even more, have more confidence in them. But thank you very much, Dr. Vera.
Okay, great, thank you. And now we open the floor for Q&A. I do see a hand raising over there. Dr. Raja, you have a question? Thank you.
Thank you so much, Professor Leo. So it was a good presentation. Dr. Arjuna. So I think the special issue here we are discussing today, we really want to focus into three aspects. That is water management, sustainability, and the food security, right? So I think it will be very nice, like somehow you bring up these issues and try to tie them together, because like I feel like this point was widely missing. Somewhat that's what I felt. And I think together with that, like, for example, okay, we are having a water crisis, right? So what kind of mechanism are there in place in the different community or societies that they are trying to come up with a solution for that? So not only looking on the agriculture productivity, also we need to look on the water sustainability, because that is the main agenda of this conferences. And I would like you to really think on this aspect, like what kind of mechanism, because there might be some very interesting mechanism that might be existing in the society itself, which, because you are doing a more like qualitative research, so you can really dig into that part. That is one part of the comments that I have for you. And another one is, maybe you could do qualitative research, but also you can do some statistical analysis together with that, using some non-parametric analysis, right? For example, there are lots of software and the tools available nowadays that you can really do that analysis. For example, like when you are making a focus group discussion, or you are going to take an interview, right? Then we can, because like when people are speaking, they are using the words, the concepts that comes out from the people's mind in the discussion. So this is kind of a deliberative analysis or the content analysis. So this kind of things can be easily done with some kind of software packages like using R, or there are also like free software packages for the content analysis. Then you can really see the linkage, like how people are building up the conversation. So what is going on? So that kind of things can also give us a more scientific look into the case studies that you are really trying to present. And this will also strengthen your paper. So I will recommend you that you take these points and then try to add up in your paper. Thank you so much.
Okay, thank you, Dr. Raja, for the comments. I think we have to move on. Once again, thank you, Dr. Arjuna, and the discussant for the interesting discussion and the presentation. Oh, by the way, dear participants, if you have any questions or comments to Dr. Arjuna, please feel free to use the Q&A section at the bottom of your screen to type your questions. And I'm sure Dr. Arjuna will be very happy to interact with you. Okay, so thank you for that. With that, let's invite our second speaker, Dr. Soyabrata Mohapatra, PhD candidate of economics from the University of Auckland, New Zealand. His topic is heterogeneous effect of climate change on crop yield and associated risks augmenting water security in India. So Dr. Mohapatra, the floor is yours. You have up to 15 minutes. Thank you.
Thank you so much for introducing me, Professor Liu. Good day, everyone. I appreciate your presence and time. The title of my presentation is Heterogeneous Effect of Climate Change on Crop Yield and Associated Risk and Augmenting Water Security in India. Climate variation and extremes pose a significant threat to steady and stable food production and thus to food security and farmer income. One such weather unpredictability is unusual rain, leading to extreme variability in water supply and agriculture. Global climate variability contributes to nearly 40% of the major yield variability, although more robust research is required to comprehend the regional implications. Certainly not all farmers are responsible to the weather fluctuation in the same way or resource depletions. This highlights the risk and uncertainty of the smallholder crop production in the tropics. Broadly, two methods are generally used, like crop modeling method and Ricardian method. However, the methods disregard the attitude of farmers towards the climate adaptation, underestimating the positive effect and overestimating the negative effect. Hence, the panel approach such as JustMark model is preferred to assess the climate effect on mean and variance of the crop yield. Study area, India ranks second in the crop production, affirming the role of water resource in agriculture, but water use efficiency in Indian farming is fairly low. And changing climate change is predicted on worsening the water crisis in areas where irrigation is mainly used to return agriculture. Of course, predictability vary to relative changes in the climate pattern. Given the growing population, Indian food security is ensured by irrigation expansion, but when combined with global warming, it lowers the labor productivity and causes revenue loss. As a matter of fact, the irrigation sector accounts for 80% of the net revenue in the water consumption, and effective irrigation is necessary for water management, since irrigation not only worsens moisture stress, but also causes groundwater to deplete. Past impact analysis did not wait on it as we respond to the gap and put up with the existing literature. We use comprehensive district level data and just crop approach to examine the effect of seasonal climate and expected yield and associated variability of 5 different crops about 3 decades in India. This paper further focused on 5 weather parameters across seasons as well as climate and extend the research by including seasonal weather anomalies, a measure of climate shocks. Since following non-weather variables could either avoid or intensify production risk, the current study also controls these inputs while estimating the production frontier. Even the water input is reinforced as the critical factor, management techniques and initiatives are revisited and prioritized. Agricultural variable has been taken from ICRISAT, namely crop-specific production area, gross crop area, gross irrigated area, and fertilizer use and agricultural labor. Crop-specific yield, the dependent variable, namely rice, sugarcane, chickpea, groundnut, bajra, is the ratio of crop-specific production to the area. Interpolation is used to generate annual labor counts for decadal labor data obtained from the population census. Because data on labor, fertilizer, irrigation is only available in the aggregate form, the pertinent crop-specific input data is constructed through prorating. Naturally, agricultural cycle differs from farming season. So seasonal climate variables has been taken from terra climate, and maximum minimum temperature, rainfall, evapotranspiration, and wind speed are relevant variables considered through IMD defined seasons, winter, summer, rainy, and autumn. Quadratic terms of the constructed seasonal weather variables are perceived to capture the potential non-linearity, and deviation of the weather variables from climate normal could also affect the agricultural performance. So that also has been incorporated. Deviation of observed weather variable from such long period average is considered normal only if the equation 1 prevails, where xid is the observed weather in district I in time period t, and xi bar is the climate normal, tau is the climate threshold. Weather anomalies omega beyond plus minus tau of xi bar capture the weather shock, taking the asymmetric response into account. To compute tau, normality of the variables are assumed, which is often adapted to find the outliers, in our case, climate extremes. Considering 99% confidence interval, climate threshold is expressed as a percentage given as equation 2. Given the last sample size as per the central limit theorem, the sample mean approaches normal distribution, and with a z-score of 99% confidence interval, post-computing tau, 40 weather anomalies of 5 climate parameters across 4 seasons is constructed through equation 3.1 and 3.2. To quantify the effect of weather variables and extremes, as per the JP method, the equation 4 represents the framework, where y is the output and x is the vector of input, epsilon as the random shocks, and beta and theta random parameters. So f function represents the expected yield, and the h function represents the variability function. So based on this, regression equation estimating climate sensitivity of crop can be written as equation 5.1 and 5.2, where xit represents the vector of seasonal weather variables. Non-weather variables have been replaced by wit, and beta, theta, gamma are unknown parameters to be estimated. To account for heteroscedasticity as well as autocorrelation cross-sectional dependence, a 3-stage generalized least square estimation is adopted for the just crop model. And in the first stage, yit is regressed from the f function and residuals are computed. In the second stage, natural logarithmic of square of estimated residual is regressed from the h function. And in the third stage, the first stage regression is re-estimated, applying the deemed weights. Detailed theoretical framework and diagnostic tests have been condensed because of time constraint. But to discern the trajectories and trend, inflection points, elasticity and semi-elasticity of these weather, non-weather, and anomaly inputs are further computed. Skipping the magnitude to simplify the discussion, increased maximum temperature harms the chickpea and sugarcane production during the winter season, while in the summer season, bajra yield is affected. Again, maximum temperature below normal climate is risk increasing for chickpea during the winter season, rice, bajra, sugarcane during the summer season. More than optimal maximum temperature leads to water loss required for farming in temperate regions, reducing root growth ratio and germination. So adopting heat-resistant varieties, increasing water transportation, irrigation efficiency are urged to solve the challenges. Increased minimum temperature damages the rice, chickpea, and groundnut during the winter season, while in the summer season, bajra, sugarcane production are hurt. Again, minimum temperature above normal climate is risk increasing for rice during the rainy season, but decreasing for sugarcane during the winter and summer season. More than optimal minimum temperature leads to wasteful respiration, dry matter, and pathogen accumulation. So changing crop rotation and enhancing the use of irrigated pest management and weather forecasts are urged to address the issues. Increased wind speed harms groundnut production during the winter, while in the summer season, bajra groundnut yield is affected, but higher wind speed impair rice and sugarcane production during the rainy season. Again, wind speed above normal climate is risk increasing for groundnut during the winter season and risk decreasing for bajra during the summer season. More than optimal wind speed leads to plant dwarfing, upgrading tissues, a rise in evapotranspiration, and root to shoot growth ratio. So maintaining grain residues, windbreaks, vegetative barrier, and increasing soil organics to improve water holding are urged to solve the challenges. Turning now to the significant water elements, increased rainfall harms bajra and chickpea production during the winter, while the summer season groundnut yield is affected. Yet higher rainfall impairs bajra and sugarcane production during the rainy season. Again, rainfall above normal climate is risk decreasing for groundnut during the summer season. More than optimal rainfall leads to soil erosion, ponding, nutrient leaching, delaying and defacing the harvest. So shifting production zones from flooded regions using flood-tolerant varieties, modern drainage practices are urged to solve the challenges. Lastly, increased evapotranspiration. It damages chickpea production during the winter season, while bajra, chickpea, groundnut are hurt in the summer season. Yet higher evapotranspiration undermines rice, chickpea, groundnut during the rainy season. Again, evapotranspiration above normal climate is risk decreasing for rice during the autumn season. More than optimal evapotranspiration increases crop water demand, drying the soil, so enabling water banks, soil cover, and increasing planting density with irrigation are urged to address these issues. The explanation of the adverse relationship between labor variable with rice, bajra, and sugarcane yield could be that marginal productivity of surplus labor in populous countries is low. Also, over-irrigation often debases soil quality, leading to water lodging and groundwater loss, lowering bajra and groundnut yield. Evidently, significant variance is shown across crops, mostly in response to the water elements with direct and indirect ramifications. Crop production is found to be more stable during the Rabi season than Kharif. Declining groundwater and biotic pressure are causes of the decreased Kharif output during the rainy season. Again, climate shocks are more likely to affect Kharif crop than Rabi. Apparently, Kharif crops, rice and sugarcane are cultivated widely, consuming a lot of water, since Indian farmers are incentivized to grow such crops under the government's minimum support price program, which strains the groundwater. The trade-off between irrigation potential created and actually used, groundwater depletion, low irrigation efficiency, productivity, and fragility to the changing climate are major challenges for India's irrigated agriculture. Initially, India witnessed three prime laws respecting water resource management, could be Water Act, Water Cess Act, and Environmental Act. Again, broad policy grounds might not accurately reflect the transformation which could have occurred in the primary sector due to climate variation. Thus, scientific solutions and techniques are proposed and arrayed alongside the federal system to retain water resource management. Extended coalition of political and scientific initiatives are provided in the paper, whereas we present only few of those. Needless to say, demand side management, social reform, farmer motivation, investment in ambiguous irrigation methods is pronounced less proactive than proven and effective drip irrigation, water accounting approach for building adaptation scenarios with stakeholders and policy legislation. The implication of the present study is consistent with the related studies, particularly CABA's 2010, but go beyond those in several ways. The effects are small, but statistically significant, which could be explained by a flat production function. Weather factors, especially water elements, have been proven to have significant effect on the production distribution, and adaptation strategies also imply the status of groundwater and irrigation, given the fact that climate adaptation often calls for increased irrigation, hence groundwater depletion. India, which experienced a green revolution in 1960s, is now in the verge of evergreen revolution, accepting the role of information technology. Yes, farmers should be endorsed as resource management communities, valuing the use of integrated natural capital. While green revolution helped India become self-sufficient in food production, it also caused various environmental and socioeconomic challenges. Additionally, weather fluctuations have opened up new avenues to the existing problem. The present study foregrounds water elements being mainly affected due to climate transitions. And on this line, Ministry of Jal Shakti was launched in 2019 to better coordinate sustainable water management. But key concern in irrigation remains the underutilization of potential medium and large irrigation projects. Inequity in irrigation dispersion has grown over time in India. In this country, a subsidy-based method to irrigate cropland by drawing groundwater has a detrimental effects on the environment. Some critical ramifications for the sustainable water use can be strengthening institutions for scaling up and scaling out inventions, aiding research innovations for effective rainwater use, supporting innovative watershed development projects, pricing blue water and entice green water use in agriculture, and relocating blue water could be a solution. Agribusiness suffers from the apathy of administrative constraints. Current investment, weak institutional-based water pricing policies are taking that toll on agriculture. So progressive involvement of the farmers in water conduct would result in conducive outcomes in terms of efficiency, equity, and economy. Thank you. Thank you so much.
Okay, thank you. Thank you very much, Dr. Mahapatra, for the interesting presentation. I do see a hand, but before we open the floor for Q&A, let's first invite our discussant, Dr. Wang Lin Ma, Associate Professor from the Department of Global Value Chains and Trade, Lincoln University in New Zealand. So, Dr. Ma, the floor is yours. Thank you. Dr. Ma, are you trying to speak? Oh, okay.
Yes.
Now we can
yes,
see
you can hear me now. Yes.
clearly.
Okay. Yeah.
Thank you.
Thank you very much for your interesting presentation. I have enjoyed reading this paper, and here I would like to share my suggestions and comments. And firstly, I would like to briefly summarize this paper. So the primary objective of this paper is to explore the effects of weather and non-weather parameters on the mean yield and the related variability of major crops in India. And this study selected 5 crops. And this study used 2 sets of data. The first set is from the district level annual agriculture data for 1990 to 2018, acquired from the International Crops Research Institute for the semi-arid tropics dataset. The second type is extensive district level weather information from the Terra Climate database, capturing monthly data from 1958 to 2019. So to facilitate the empirical analysis, this study employed the statistic frontier analysis model. And the study found that seasonal weather variables have a significant influence on expected production, and associated production risks are explained by weather events And then below are my suggestions and some questions. Firstly, the suggestions. Firstly, I think in the abstract section, it's better to clearly indicate how seasonal weather variables affect crop production, like to say positively or negatively. Because in the present study, it just briefly mentioned that seasonal weather variables affect crop production, but after reading, we have no idea how it influences the crop production. And in the introduction section, I have two suggestions. The first one is to cite more papers published in recent 2-3 years because the literature in this field is very rich. However, by reading the present paper, we can see the papers cited in the introduction section is old in general. So discussing the introduction section based on the recent literature can help to show the authors are doing the cutting edge research. And the second one is to clearly discuss the contributions of this study because objective is different from contribution. And the third suggestion is, I think it might be useful to add a background section to compare the outputs of the crops discussed in this study, including rice, bajra, chickpea, groundnut, and sugarcane. So this study analyzed these 5 types of crops. And from the FAO statistics data, you can also find the data information from other countries, which also produce these crops. So by adding some information and comparing the production of these crops in India and other countries, so we can clearly understand the status of production in terms of these 5 crops. In the data section, I think it's better to include more discussion about the data, agriculture data. And currently, the data section is very brief. And the next one is results section. I think it is important to clearly mention which equation you have used to generate the empirical results, because in this study, you have discussed many formulas or equations. So in this case, it's better to clearly indicate the equations used to generate the results. And the discussion and implications section, I have one suggestion here, and I would suggest that you move the implications to the final section. After discussing the conclusions, you can discuss the policy implications or recommendations, because normally we discuss the implications in the final section after discussing the conclusion section, and then we discuss the implications of this study. From my side, I feel it's very strange to discuss implications when discussing the results. Okay, so these are some suggestions. And here I have 3 quick questions. The first one is agriculture data was sourced from 1990 to 2018, while climate data was sourced from 1958 to 2019. So how did you merge the data for empirical analysis, because they are sourced from different year periods? This is my first question. The second question is, have you considered conducting the disaggregated analysis to explore the regional differences in terms of the effects of weather and non-weather variables on on yield. And this can improve the policy implications, because for different countries, the impact might be different across the geographical locations. Okay, so my third question is, stochastic frontier model is mainly used in this study to estimate the technical efficiency of crop production. And then this study mainly used the stochastic frontier model to analyze the factors affecting the crop yield. And the factors mainly include the seasonal weather variables. So because this study did not calculate the technical efficiency of crop production, so in this case, why don't you use ordinary least square regression model, which can directly help you to achieve the estimation goal? Okay, that's all my suggestions and questions. Thank you very much.
Okay, thank you very much, Dr. Ma, for those comments and the suggestions. I'm sure they are appreciated by the presenter. And before I ask Dr. Mahapatra to respond, how about I collect one more round of questions or comments? Okay, so Dr. Paria, I see your hand rising over there. Thank you, Dr. Paria.
Thank you. Thank you, Dr. Mahapatra, for this nice presentation. So my question is what the discussion Professor Walling Ma asked regarding the data. What I know, India did not publish any data like crop specific fertilizer and crop specific data related to labor. So if I may be wrong, but if you use share of area, like if you take the share of area for the specific crop, and if you get that weightage and you calculate the labor and fertilizer, that will be a wrong method to calculate it. You know that composition of labor use and also lots of other things are there to use it. So if you use it, you have to rethink about it. That is my question. Please clarify me.
Okay, thank you, Dr. Paria. Dr. Mahapatra, would you like to respond to their comments and the suggestions? Very briefly, thank you, sir.
Thank you so much, Professor Ma and Vidur. Really helpful comments. And thank you so much, Professor Ma, for reviewing my paper. So I would first answer 3 of your questions about the data, specifically the change in data for the agricultural and the weather data. So when we are doing a panel data analysis, we take data from different years. When we do it in the software, so it automatically deletes the data that has not been there systematically for all the variables. So it is automatically dropped. But as a data sourcing, we mentioned that this data has been taken from this period to this period, just for the broader picture. For the second question, of course, yes, regional analysis is really an important thing. And I was currently doing a spatial analysis using spatial econometrics on the same ground. And of course, in this study, we are not using proper spatially disaggregated regional analysis. Rather than we're taking it as an aggregate, as whole of Indian geography into the picture. But yes, I of course want to do some spatial analysis on this ground. And about the OLS method, using the OLS method, because in this paper we had like 80 variables. We tried to look at the expected yield. We tried to look at the production risk and all those things, uncertainties like creating anomalies, or these things cannot be incorporated or encompassed in one simple OLS model. It will not give you the variability towards the production risk or anything. It will just give you the simple figure for the variable. So to extend or enrich our model, we have chosen the hybrid stochastic frontier method so that we can have more results, more prominent results, rather than having simpler one. And about the abstract, it was in the journal instructions that it has to be 100 words. So I had to shorten it, and but if they allow me, I'll definitely put some more instructions there. Like it was only 100 words. So, and of course, I will definitely try to look into some recent literature to put up, like comparing other developing countries. I have already did that. Like for table 1 and table 6, I have provided extensive literature review that is in the separate table file. About the data, yes, I have put 2015 district boundary data, which I have precisely included in the data set, but I can definitely elaborate it a little bit more for clarification. And equations are developed like from the theoretical framework. It's like a step-by-step, like we have done it like from this equation, how we are reaching this equation. It's like through the process, which I would say I have done that, but if directly the equation that has been estimated, the functional form is preferred, that also can be incorporated. And yeah, that's the things I was writing down as you're saying. So thank you so much. And yeah,
Okay.
yeah.
Thank you
so much, Professor Liu.
Yeah, thank you. Thank you very much for the responses. And now let's see, is there any other questions or comments for Dr. Mohapatra? Please use the raise hand in the chat box. Do we see any questions? I do not see any hand. It seems that you have
one more question from Bidu.
Oh, one more. Okay. Yeah. One more question.
Yes, my
Okay, go ahead,
question
please.
actually, can you please elaborate that my old questions, like how you calculated the labor and the fertilizer?
Wow. Okay, I forgot. Okay. So there is a method called prorating. So prorating is like we take the aggregate value by proportion of the area under the crop, which we are selecting, is expressed as a tons per hectare. So it's through the prorating method, crop specific variables have been obtained. And similarly, the crop specific inputs have been obtained. But obviously what you're saying is correct. Aggregate variables are only out there. We have to construct the variable of your interest.
My suggestions was like, if you use the area specific sayer, that will be methodologically a wrong method, because lots of scientific papers, agriculture department, they are published, like what should be the appropriate fertilizer proportion and what actually people are practicing. Lots of recent literature have been published. You can go through it. From there, you can segregate the fertilizer, how you use the fertilizer on crop specific fertilizer, and from there you can segregate it spatially. Spatial econometrics can solve this problem, but in that extent you can use it. And also in case of labor is really a dangerous thing. Like you are dealing with that labor, and it's a agriculture labor, and you are taking it from census and you are segregating it. And right now, that because of the mechanization in agriculture, harvesting and everything, the cereals crop, they are not using that much labors also. And you are putting, because the share of area is too much for those crops, and you are putting too much labor into that thing. So whole analysis will be wrong, whatever result you will get from there. And I'm seeing that all of the results are significant. So please think about it before doing your final conclusions. That is my suggestions.
Okay, thank you. Thank you so much for your suggestions, Bidur. So one of other papers, like we have seen on this line, when we don't have a crop specific variables, to omit any sort of bias from our estimations when we're doing a hybrid stochastic frontier, we have to do something like this that covers the entire geography, because we're not only looking at one specific area of India, we're entirely looking at whole India, right? So if you're taking an aggregate variable, how to find the crop specific inputs or outputs? Prorating. That's the only method we can do, or we can refer it, as this is the prescribed method done in the previous literature, because crop specific variables are not there as data limitations. So to conduct this research, yes, we have opted for this one, and the results are significant because it is accurate. Like if you have if you have gross proportion area to total aggregate value is divided, it will give you the crop specific variable. So, and that is like one method I have seen a lot of people doing, but it's more, I would say, stochastic frontier, using stochastic frontier or more advanced methods, or putting up to the water foreground, because the implications of this conference is for water and food security under climate change. So putting everything together, I don't think any other research has contributed on that aspect. So it will be, I would say, okay, but yeah, thank you for your
Actually,
suggestions.
the problem
I
is
will
happening
definitely
here.
try to answer
Yes,
some
yes.
of these questions. Yeah.
Yeah.
Okay.
Thank you.
Yeah. Okay. Thank you. Thank you to both of you gentlemen. I really enjoyed this heated discussion, and I find it really interesting. So any other question? So Dr. Mahapatra, I myself do have a quick question for you. Okay. In the introduction section, you talked about water sensitivity across crops. So I was wondering whether there has been any research out there that has examined the water sensitivity across different seasons by crops. For example, in terms of the rice, right? So different seasons or different stages of growth, the sensitivity to water might be different. I'm not an agronomist, but I'm just curious whether there has been any research like this out there. Thank you for that.
Yes, I mean, of course, the water sensitivity of each crop in each season is different. And that's why I have done a seasonal analysis rather than an annual analysis. About the sensitivity, the degree of sensitivity of each crop to water susceptibility. And that thing, I would say, I have just drawn it from our past literatures, from my literature review. Like I can say rice and sugarcane is a water intensive crop. So this is just like a brief statement. I haven't tested for it or examined on that ground, but I have taken it from the literature and looking at the sensitivity aspect, including climate variables and other control variables, and looking at the final results. So that was my outcome. So the aim of the paper was to check the climate sensitivity of agriculture, food and water security. So different crops with different degrees of water sensitivity was taken, which was further divided into Kharif, Rabi, that's your monsoon crop, or winter crop. So different weather and non-weather inputs were also used to enrich the model. So again, as I say, like we have run many models and noticed the water related inputs have been consistently more sensitive for each of the crop, and accordingly we have interpreted the results with the proper policy implications, both scientific and federal governments. Thank you so much, Professor Liu. Thank you so much.
Thank you. Thank you very much for the response. Okay, according to the program that I have at hand, I think it's break time, right? Yeah, there will be a 30 minutes break, so which means that we will reconvene about 58 minutes from now. Okay. Oh, by the way, during the break, if you have any comments or suggestions for our two presenters or discussants so far, please feel free to leave them in the chat box, and I think we can continue the discussion after the presentation section. Okay, Dr. Dio, is it break time?
Yes, thank you so much, Professor Liu.
Okay, thank you very much. Okay, welcome back to the afternoon session. So in the rest of this session, we're going to have 3 more interesting papers. Without further ado, let's invite the presenter for the next paper, Dr. Tiyasa Mishra. research scholar from the Department of Humanities and Social Sciences, Indian Institute of Technology, Kharagpur, India. The topic of her presentation is climate variability, rainwater harvesting structures, and groundwater level in Odisha, India, and empirical analysis. So Dr. Mishra, the floor is yours. You have up to 15 minutes. Thank you.
Thank you for giving me an opportunity to speak from here. So I'm sharing my screen. So, is it visible?
You're good. Go ahead, please.
Yes. So, yes, so I'm going to speak on the topic climate variability, rainwater harvesting structures, and groundwater levels in Odisha, India, and empirical analysis.
Yes, sir. Do you mind pulling to full screen, please? Thank you.
Yes, ma'am.
So there is a button, the right bottom. So you
Yes,
click
the right button.
Yes, that's right.
Yes.
So is it visible
now?
No, button.
There's the button. Go
Just
ahead,
next.
Dr. Gill.
Yes, actually the button on the top, I think it's not.
No, button at the
visible.
bottom. It's at the bottom. Next to that, next to that. No, front.
Next to the minus. Next to the minus sign.
Next to the minus, yes.
Yes, great. Okay, great. Go ahead, please.
Yes, so I'm going to present on the topic climate variability, rainwater harvesting structures, and groundwater levels in Odisha, India, and empirical analysis. So around 85% of the global rural population depends on groundwater for a variety of domestic as well as irrigation purposes, according to the World Bank data of 2010. India, being one of the largest users of groundwater resources in the world, around 60% of the Indian districts have already shown evidence of either groundwater depletion or contamination, or a combination of both. So India extracts around 230 cubic kilometers of groundwater per year, according to Central Groundwater Board in 2014. More than 63% of agricultural land in India is irrigated using the groundwater. In arid and semi-arid regions, 60 to 100% of the water supply depends on the groundwater itself. Now, coming to the causes of the groundwater depletion, water-intensive, high-yielding crops like rice, they use a lot of water. Rural electrification, like there are several electricity subsidies due to which more and more of groundwater is extracted. Urbanization and industrialization, uneven rainfall, increasing population, and the declining cost of installing the pumps. So in 2022, Odisha has faced more depletion in the groundwater level due to the whooping 47% of the rainfall deficit in the last 2 quarters of the year, mainly due to the less amount of moisture-based winds flow from the Bay of Bengal. The improvement of the well productivity by recharging the groundwater can be beneficial to the farmer associated with the tanks. Now, these tanks are mainly the man-made structures which are horsebow shaped, size of about 1 to 2 acres to 50 to 100 acres of land. These are created to harvest the rainwater during the rainy season, and these rainwater harvesting actually helps to improve the groundwater level through percolation, and also it is used for the irrigation purposes in the summer season. In the tank dominated and the drought prone regions, people mostly depend on wells for the water. Loss of tank capacity is likely to cause the degradation of the tanks, and at the very same time, this may result in the loss of the groundwater recharge. So there are a very limited number of empirical studies that explored the relationship between the traditional water harvesting structures and the groundwater depletion using the macro level data in India in general, and for Odisha in particular, these number of studies are very limited. However, the studies which are available have not classified the districts on the basis of the vulnerabilities. Coming to the objectives, the first objective is to identify and analyze the factors responsible for the depletion of the groundwater levels and to establish the associated links between the surface and the groundwater in Odisha. Now, this diagram, which we can see here, basically focuses on the relationship between the groundwater level and the number of rainwater harvesting, that is tanks. So this orange colored line, it shows the number of tanks, and the blue colored line shows the groundwater level MBGL. So we can see that there is a positive relationship between the two. So we can see here the location of the state of Odisha, and Odisha is a state which uses around 16.69 lakh billion cubic meter of the groundwater resources, according to the data of government of Odisha in 2017. During the April 2019, the water level in the state varies from a minimum of 0.11 meter below the ground level in MBGL in Anugul district to a maximum of 15.60 MBGL in Koraput district. This water level should actually have been within the range from 2 to 10 MBGL. So these are the 10 agroclimatic zones of Odisha. You can see in the diagram. So coming to the study area description, in Odisha, the irrigation ratio was around 38.4 in 2014-15 compared to 48.6 at the all India level. Odisha's ultimate irrigation potential is about 8.8 million hectare, out of which 3.6 using the major and medium projects, 1 using the minor flow, 4.2 using the minor lift irrigation projects. More than 80% of minor flow had been exploited, according to Government of Odisha data in 2019. Until 2016-17, only 64% of the irrigation potential has been utilized, and showing the declining trend in the minor irrigation scheme. Now coming to the methodology part, so there are basically 4 steps. First, we have collected the data related to the geographical aspects, then grouping of the districts to understand the role of the different parameters. Third, specification of the econometric model used in the study. And fourth and final, the dynamic panel model estimation on the determinants of the groundwater depletion. So this table shows the rainfall, forest cover, rice cultivated area, net area sown more than once, groundwater depth, district gross domestic product, number of tanks, and tube well irrigated area, taking the average of the years from 1995 to 2017 in different districts of Odisha. Now, this study uses the dynamic panel data model based on the generalized methods of moments developed by the Arellano and Bond in 1991. So there are several parameters, classification, and the criteria used in the study. So first is the climate change, based on which districts are classified into drought and non-drought prone districts. More than 10 droughts since 1901, this means that it is a drought prone district. Otherwise, it's a non-drought prone district. Tribal and non-tribal districts, more than 50% tribal population means it is a tribal district. Otherwise, it's non-tribal. Saline water intrusion classified into coastal and non-coastal districts based on the location of the districts. And finally, the economic development into low, medium, and high district domestic product districts based on the size of the district gross domestic product. Now, here is the number of districts in each category. So you can see here the low GDP district, the medium GDP districts, and high GDP districts are 11, 9, and 10 respectively. The tribal districts are 8 in number, non-tribal 21, drought-prone districts 19, non-drought-prone districts 10, coastal districts 7, non-coastal districts it's 22. So basically, if you want to calculate the interval, it's highest DP minus the lowest DP, taking the number of classes in the denominator. And so based on this, we can divide into the low DGDP class, medium DGDP, and the highest DGDP class. So here is the equation, which the functional form which has been used in this study, that is the depth of groundwater, which is a function of the forest cover, net area shown, the area irrigated more than once, rice cultivated area, literacy rate, population density, number of tanks, tube well irrigated area, annual rainfall, and the district gross domestic product. So here are the data sources and the data available from these sources. So coming to the descriptions and hypothesis of the variables used in the models. So one dependent variable has been used here, that is depth of the groundwater level. And accordingly also, like the independent variables which have been used here are 1 year lag of the depth of the groundwater level in MBGL positive hypothesis, area under forest cover in hectares and net area zone is negative, area irrigated more than once and rice cultivated area positive, literacy rate is negative, population density is positive, number of tanks is negative, too well irrigated area is positive, average annual rainfall as well as 1 year lag of annual rainfall is negative, and district gross domestic product it's positive. So in some cases lag has been used. It means that the measurement has been done based on this year as well as the previous year. So coming to the results, that is a lag groundwater level is positively and significantly associated with all the estimated models except for the drought prone districts. As the area under the forest cover increases, the groundwater level tends to improve in the drought prone district and the medium GDP districts. As net area sown, that is the area in which the total crop grown increases, it means the groundwater level improves in the pooled, that is the overall, drought prone, tribal, non-coastal and the medium GDP districts of the state of Odisha. So here this table shows the significance. The groundwater level has been noted by GW, it's MBGL. So the red colored boxes and show that these are negatively significant, and the blue colored boxes means these are positively significant. So the dependent variables have been listed, and accordingly the overall Odisha drought prone, non-drought prone, tribal, non-tribal, coastal, non-coastal, low DGDP, medium DGDP and high DGDP districts are mentioned here. So this table shows the number of observations, the walled chi-square values, the probability greater than chi-square, and the number of instruments also. And Arellano bond test has been conducted, and based on that, the results have been shown in this table, and also the mean VIF. Coming to the results, districts with more area irrigated more than once, the groundwater level tends to decline. As the area under the rice cultivation increases, the groundwater level tends to decline. With rise in literacy rate, the groundwater level is likely to improve in the pooled tribal and non-tribal districts of the state of Odisha, which means that if people become more and more literate, they are likely to use less amount of groundwater. Population density is positively and significantly linked with the groundwater levels in the pooled tribal, low and high GDP districts. So which means that if increase in population is there, then people are likely to use more amount of groundwater. The presence of number of rainwater harvesting structures, that is tanks, is negatively and significantly associated with the groundwater level. Too well irrigated area is positively and significantly associated with the groundwater levels in all the models except for the coastal and the non-coastal districts. Annual mean rainfall is negatively and significantly associated with the depth of the groundwater levels. Coming to the conclusion, the average annual rainfall, presence of the number of tanks, forest cover, and net area sown are positively influencing the groundwater levels. Area under the tube well irrigation as well as the rice cultivated area are adversely affecting the groundwater levels in the state of Odisha. The estimated models indicate a strong relationship between the rainwater harvesting structures, that is surface water, and the groundwater levels. Both the groundwater and the surface water sources have to be used very judiciously in order to maintain the hydrological balance between them for the long-term sustainability. So here we can see the references used in the presentation. So that was all about my presentation. Thank you.
Thank you. Thank you, Michelle, for the interesting presentation. Now, let's invite our discussant. Oh, he just made the presentation in the previous session before the break. So, Dr. Soribrata Mohapatra, PhD candidate of economics from the University of Auckland, New Zealand. So, Dr. Mohapatra, the floor is yours. You have up to 10 minutes. Thank you.
Thank you, Professor Liu again. And I appreciate the chance to discuss this interesting paper. The title of the paper is Climate Variability and Rainwater Harvesting Structures and Groundwater Level in Odisha, an Empirical Analysis. The study seeks to identify and analyze factors responsible for groundwater depletion in Indian state of Odisha. Applicability of the study area is well explained. Examines the link between traditional rainwater harvesting structures such as tank or surface water and groundwater recharge. The author indeed have referred a good number of literature. The introduction does explain the subject, purpose, and the plan of research, but could explain the relevance of the climate variability. Using district level secondary data from 1995 to 2017, a dynamic panel regression model based on GMM has been estimated in order to identify the determinants of groundwater depletion. The equation of interest is depth of groundwater as a function of forest cover, net area shown, area irrigated more than once, rice cultivated area, literacy rate, population density, number of tank, tube well irrigated area, annual rainfall district GDP. I think evapotranspiration rate and rice specific area could also be incorporated. The author could clarify if the decadal census data is interpolated with respect to the population growth. The results show that average annual rainfall, presence of number of rainwater harvesting structures, forest cover, net area shown are positively influencing water level, groundwater levels, whereas the area under tube well irrigation and rice cultivated area are adversely affecting the groundwater level in the state. Heavy rain raise groundwater and favor yield, but heavy irrigation depletes the groundwater and disfavor the yield. In addition, positive influence of surface water harvesting structures on groundwater table in all the estimated models indicate a strong link between the rainwater harvesting structures and groundwater levels. However, the results and conclusion doesn't tally. For example, the paper states that literacy level of the population in the district have turned out to be negatively and significantly related to the groundwater level in pooled tribal and non-tribal district models, which imply that with the rise in literacy rate, the groundwater level is likely to improve. This may be due to the fact that literate people tend to be more aware of the problem of groundwater depletion, hence tend to adapt rational use of groundwater resources, limiting its excess extractions. So the negative relation between two variables should indicate inverse relation, but the study reports direct relation. Similar other inconsistency could also be observed and modified. The information is certainly presented in a logical manner, but the gaps in the existing literature could also be justified. Given the reasoning, the concept of climate variability could also be brought out clearly. Following the panel data, pre-estimation diagnostic test could also be supplied to enrich the model specification. The paper has tried to address an appropriate issue of depletion of groundwater in Odisha. The title is promising, though the findings or suggestions are generic in response to the existing literature. The emphasis could be streamlined towards the agriculture and food security alongside water security. In fact, the study by Chaudhary and Behera 2018 is declining groundwater level linked with the discontinuity of traditional water harvesting systems, tank irrigation. Empirical evidence from West Bengal published in Groundwater for Sustainable Development had explored a similar findings in similar state of India. The current paper looks similar and address some of the issues which is already discussed. However, as the author could bring the concept of climate variability and its impact on food and water security, adequately discussing the context of previous research on the related subjects, the paper could be a significant contribution to the existing literature. Thank you so much.
Thank you. Thank you, Dr. Mohapatra, for your comments. Dr. Mishra, would you like to respond briefly to Dr. Mohapatra's comments? Thank you.
Yes, thank you, Dr. Mahapatra, for such comments. We'll surely try to incorporate this in our study. So some things I want to mention are that obviously we would like to add some more factors to the functional form, as you have mentioned. And also, like the data has been taken at the average of the years from 1995 to 2017. As you have mentioned regarding the climate variability issue, the rainfall issues have been considered here as the climate variability, and it has been already mentioned in the study. So there are obviously some other factors which I've mentioned, and we'll surely try to include that in our study. Thank you.
Okay, thank you. Now we open the floor for Q&A. Any questions or comments for Dr. Mishra? Oh, I do see a rising hand. So Dr. Raja, please.
Thank you, Dr. Leo. Yeah, I think it was a very wonderful presentation. I think you have really kept nice studies on the climate variability and the water resources. However, I think the some suggestion and the comments that I have for you is when I listen to your presentation, I think there is a bit of missing part on the sustainability part, because what is the kind of the proxy that you're using for the sustainability, or how you are even trying to address the sustainability in your model first? So I would like to hear from your side, like what are your strategies that you are going to deal with the sustainability issues in this paper, and how you are going to bring it. And I think also because like water is not only the current problem, it has the intertemporal issues and it has the intergenerational issues. And I think that needs to be well addressed in this paper. And as given this is a conference, main focus is on the climate, food security, and the agriculture. So together with that, I think we cannot miss out the part of the sustainability. And I would like to hear from Tiasa, like what are your strategies and what are your the opinion that how you are going to accommodate these features in your paper, and how you are trying to bring it up in these issues. Could you like to please explain on this part? Thank you.
Okay, thank you, Dr. Raja. Dr. Mashra, do you have any quick response to Dr. Raja?
Yes, thank you, sir, for such beautiful comments. And actually, for the sustainability issues, we have not mentioned very theoretically very much in our paper. We have only tried to write the results and explain the results based on the empirical part, the results which we have obtained by doing the analysis. So based on that, we have tried to mention some of the issues, but yes, obviously we will try to incorporate some more ideas and try to explain it in a more theoretical manner.
Okay, thank you very much for that. And for the sake of time, I think we'd better move on to next presentation. So the next presentation will be on the impact of climate change on wheat productivity and the role of irrigation in saline soil environments in Uzbekistan. This presentation will be given by Dr. Ihozho Bobojonov, a senior researcher from the Department of Agricultural Markets, Marketing and World Agricultural Trade, Leibniz Institute of Agricultural Development in Transition Economics, Germany. So Dr. Bobojonov, the floor is yours.
Thank you very much, Dr. Xiaofang Liu. Thank you very much. I will try to share my screen now. Hopefully it will work. Hopefully it will work out. And then I try to go to full screen now. Hopefully you can see my screen now.
Yes, great. Go ahead, please.
Yeah, thank you. Thank you very much for giving us an opportunity to present this study. Thank you, Dr. Xiaofang Liu, for your nice introduction. I have shortly introduced the other co-authors because this paper is mainly done by Mashkura Babajanova. She's a PhD student of at the Tashkent State Agrarian University, and at the same time she's a fellow at our institute. And then I'm co-supervising her with Dr. Lena Kuhn and Professor Thomas Glauben, and she is currently busy with her defense at the Tashkent State University, and therefore I'm presenting this this work on her behalf. The title is as you announced, the impact of climate change on wheat productivity and the role of irrigation in saline soil environments in Uzbekistan. I will drop this, and a most important issue, most important motivation of her to take this topic is that the climate change impacts on crop yields and its productivity, because the studies in the region show various analysis in most of the cases. They of course confirm each other, but not in all cases. There are some studies who are showing various directions, but all studies have a one common agreement. Even they find a negative or positive impact, it might not be their agreement, but the agreement that the impact is there. I mean, it's not expected. No one expects that the yields will remain same in the coming years. They all agree that the temperature, precipitation, water availability impacts on, in fact, yields, and of course the majority show it as a negative impact. And this, of course, will challenge the food security, because most of those countries are very much dependent on agricultural production in the region, most of the Central Asian countries. And then the availability of the food, of course, is very much affected from the future project that changes. And as long as the availability of the agricultural products also change, the price of the products and supply of agricultural products are also dependent on this, because especially the Uzbekistan is a landlocked. The local production plays a very much important role, and therefore it might have a very much negative impacts on it. As I indicated, this is a landlocked country, surrounded by so-called stans: Turkmenistan, Kazakhstan, Tajikistan, Kyrgyzstan, and Afghanistan, and do not have a direct access to sea. And the temperature is very continental, and then it can reach in -35 in north, and +50 is also possible in the south. It's very continental temperature. Here you can see some trends compiled from the World Bank Climate Change Knowledge Portal, and here it's very clear that the temperature is increasing. There's no doubt about that. It's very clear. And then the precipitation, of course, precipitation also increases. I mean, one might think that if the precipitation is also increasing, if you look at this graph, it might be a good, because I mean, it might give some impression that in a dry area, if the precipitation increase is a good, but that's not the case, because if you see here, we are speaking about like, I don't know, the average precipitation of 180 or 190 millimeters, and it's still not enough. It's still not enough for to cover the evapotranspiration of plants, and therefore this is not enough to cover the water demand of crops, and therefore even there is an increase, it will be easily offset by the increasing the temperature. And therefore, because of the low precipitation, the country is very much dependent from irrigation water, and that was the main reasons why we also took the irrigation availability. And main products are cotton and wheat. As you can hear, the distribution in 2018 about 34.6% of the area is allocated for cotton under irrigation, and about 40.6% is allocated to wheat. This is mainly, I mean, the cotton, because of these two crops are high share, it's related with some kind of historical developments. In the Soviet Union times, the Uzbekistan was the main cotton supplier, that the very, very large area was covered with cotton. But afterwards, the country want to have a food security, and then want to have some kind of secure supply, and therefore of grain crops, because bread is a most important crop in the daily diets, and therefore like state want to have under different crisis scenarios, under different fluctuations of the wheat supply in the international markets, and want to have some kind of security, and then increase the production of wheat, and therefore wheat became another major crop in the past. And state played up to now, state played very much role via different forms of procurement, that these two crops remain most important crops in the cropping crop allocation decisions. So if you can see here the trend of production of harvest area of wheat here, which is our important crop for today, we are going to discuss, and then the blue line is a wheat. As I indicated, because of this food security policy, the harvested area increased very much, as you can see in the red line, and stabilized during the recent 10-15 years. However, you can see the fluctuations in wheat yields, and then there are very much fluctuations in a wheat yield, wheat productivity, which is again back to our main motivation topic on the climate change, as well as availability of irrigation water. Another important issue we have to think here in case of Uzbekistan. Many of you, I mean, might have been working in other Asian countries and might not have a very detailed information on the environment of Uzbekistan, but all you might have heard about so-called Aral Sea crisis. Yeah, you might all heard about the disappearing Aral Sea or disappeared. I mean, this does not exist anymore, or almost does not exist. And therefore, you might heard about it, and then this also had a tremendous impact on the environment. In some regions, the salinity here is most important. Is here in this graph is the soil salinity. For example, if you look at the Karakal, Pakistan, or Kharizm region, these are very located close to this Aral Sea region. The salinity is very high. Also, some regions of Sirdarya, those are very high soil salinity. And then some regions you can see here, like a Tashkent region or Surkhandarya, then the soil salinity is relatively low, and therefore this is not only the challenge, the climate change, but the soil salinity is also becoming an important factor to consider it. And therefore, the impact of the objective of this study was just to analyze the impact of climate change on wheat productivity, but take into account also irrigation and also in the context of saline soil environments, and to analyze the impact on those factors. The Mashura took like 170 districts in Uzbekistan for the years of 2008-2017, where she can get the data. It's a district level data, and from this 117 districts, like 158, the districts had a full data set, because she has to collect the data from regional agricultural departments and the regional water departments, and therefore in some regions are not, some districts are, of course, some of the data is not available, and therefore it's like complete data set consists of 158 data
Sorry
set.
to interrupt. Sorry to interrupt, sir. You have about 3 minutes to go.
Oh.
Thank you.
Okay, good. I will speed up now, and because it was I was thinking that I have a presentation between 8 and 8:15, and therefore, okay, I look at the clock. Okay, I will speed up now. Okay, they take the data because it's difficult to get data for the hydrological data and temperature data for the case of Uzbekistan, and we replace it with satellite combined data, and then for further interests, and we have developed a kind of platform where researchers can get any locations of the world. We can, if you're interested, I can. Okay, I dropped some of the slides because it's just a simple Cobb-Douglas production function and land labor capital and inputs. She used a fixed effect model. It's only important to have a look at, as the previous presenters also indicated, that we have like divided the temperature and into seasons. Like we have like a spring, autumn, summer, and winter seasons, because they are the impact could be very various depending on it. And additionally, we also have here soil salinity, availability of irrigation water, and the descriptive statistics. I will not spend now too much of time, and just to shortly mention that there is a very large variation in the data set, I have to say, because from one edge to another edge, the country is about 1,500 kilometers, and then you see various in case of temperature and climate. And the only important issue to mention that this is that we use the total production of wheat as a dependent variable, and then total use of irrigation, land labor in independent variables. Here is her main results, and you can see land labor fertilizer is very significant, and irrigation water is also significant, but significance level is not as strong as land labor fertilizer or some temperature or precipitation indices, or the soil salinity. Without going too much of details, mainly could be explained. We can explain it mainly because of the irrigation water use efficiency. Because irrigation water use efficiency in the region is still not very high. The results show it's still important irrigation water availability or use, but still there are some problems that the irrigation efficiency need to be improved. And then groundwater or the soil salinity we are interested in also has a negative impact. If I summarize shortly, is that yeah, the variation is the vulnerability of heat to precipitation and temperature changes. There in the presentation above, there was a comment that should be detailed on the impact, positive or negative. Here we try to say that in it, like spring and autumn temperature, we see a positive contribution but summer temperature has a negative because of the summer temperature, mainly explained by like kind of temperature stress. Like in summer, if it's too hot, then the wheat yield may lose grain. Irrigation may support the productivity, but it's a problematic in the region. Is the water use efficiency need to be improved, and then soil salinity has a negative impact. It should be taken into account. Short, some policy implications are there that the region has to improve water and soil management mechanisms sustainably, and the one important issue is the extension services, what we have discussed in more detail in the scope of the paper here. Not too much time to link it with it. And again, in the water use efficiency, we have to say that need to be considered very much. And our results show that especially the summer temperature should be a problematic, and therefore like more tolerant, more heat tolerant varieties should be improved, and also the role of residue retention should be more considered in the policy making in the coming years. That's shortly, if I can summarize the study of Mashura Bobajanova, and I try to answer to your questions as much as possible, but if you also have very detailed questions, I put her address below, and then you also may contact her directly. Thank you very much.
Okay, thank you very much, Dr. Bobajanov, for the interesting presentation. Now, let's invite the discussant for this paper, Dr. Xiaomeng Cui, Associate Professor from the Institute for Economic and Social Research, Jinan University, the People's Republic of China. So, Dr. Cui, the floor is yours. You have up to 10 minutes. Thank you.
Thanks, Chengfang. Can you see my slides?
Yes, very clearly. Go ahead. Thank you.
Okay, thanks very much, and it's a great honor to be part of this session and also to serve as discussant for this very interesting paper. It's a paper about the impact. Oh, I probably should full screen.
Yes.
It's a paper about climate change and also irrigation and soil salinity. And essentially, these are three very important environmental factors that matter for agricultural production, and not just in Uzbekistan and also in other parts of the world. And let me just briefly summarize. So the empirical strategy is a panel fixed effects estimation at the district level, and the panel covers roughly 10 years. And essentially, identification comes from exploiting the within variation in environmental factors. And the authors have shown that there's rich variation in the data set. And the main results tied to the three different environmental factors. The first one is that the temperature effects, which is at the core of understanding climate change impacts, and thus has a seasonally differentiated effects. So basically beneficial in spring and fall, but detrimental in the summertime. And the next point is that irrigation water use is going to enable adaptation. And the last point is that soil salinity is going to lower crop productivities. All those results are qualitatively very straightforward, but still the quantitative results are very important for policy discussions. And clearly this paper has a lot of direct policy implications. For example, as the author pointed out, improving soil and water management in similar regions, not just in this country, is going to be very important for sustainability, especially under the threat of climate change. And also the paper is going to highlight that there's combined effects of climate change and soil salinity, soil salinization. And this is very important because although we have a lot of discussion on climate change, but there's not enough discussion on the issue of soil salinity, but it's critically important, especially for countries on the coastal part of the world where you have seawater rise and also the seawater salinization. Although it's not the case in this particular country, but the implication is going to be generalized to other country contexts. So the general assessment is that this is really important research and with very high policy and practical relevance, and focus on the country which has received relatively little attention compared to other places like the US or even China. And also the implication can be generalized to other places around the world. Here I'm going to offer a few suggestions that could potentially improve the empirical part of the paper. The first point is about that there could be more flexible specification on the, especially the temperature effects. So the literature has talked a lot about nonlinearity and temperature response. So in this particular paper, author choose to use seasonal average temperatures, but there could be other design that construct bins or degradés that directly capture this nonlinearity. And I put the reference here, Sri Lanka and Roberts, which has a lot of details on how to do this. And also on the soil salinity, water salinity, there could be alternative measure that use a threshold variable. So it means that after getting or get over a certain threshold, the damage could be very severe. So this is something that can be potentially used for further detailing the effect. And the second point is that a nice part about this paper has a lot of information related to inputs. So with that information, the authors can actually look at something like a TFP rather than just looking at yield. And this could have different implications on how we understand the change, the impact of climate change, irrigation, and also soil salinity. And I put a reference here as a paper by Shuai Chen and Bin-Lei Gong, recently published on JDE, and they use the Chinese context to look at both TFP and yield effects. That could be a useful reference. And the third point is that there could be different perspective for understanding the role of irrigation. So here in the current model, it's just a level effect. It's a separate variable in the regression, but that could also be a slope effect, meaning that you can compare places with irrigation with places without irrigation to see if their sensitivity to climate change and soil salinity are similar. And one of my own paper has something like this, and this could be a reference. And the last point is that the authors could come up with some ways to contextualize the estimated impact. So one thing I can think about is a back of the envelope calculation, where you can bring the negative impacts identified from your empirical results to multiply some with some monetary numbers so that you can have a direct measure of the monetary values that was reflect the damage that's caused by those environmental threats, so that it's easier to communicate how large are these impacts. And in the end, I have a few more suggested references tying to the three environmental factors. The first one is about climate change impacts, and these two are just survey articles. And the second one is about the role of irrigation, and these are some of the conventional discussion on why we need to compare places with irrigation with places without irrigation. And the last point is about soil salinity. Those papers are not focusing on climate change, but only focusing on soil salinity. But I feel that they are important papers in this literature, so maybe it's worth checking the details in those parts. So these are all my comments, and it's really nice presentation and really nice work. Thanks.
Thank you. Thank you very much, Dr. Tsui, for your comments. And that's so nice of you, not only offer comments, but also at least the detail, the references. That's really helpful, I'm sure. They're also appreciated by the presenter and the co-authors. Okay, before we collect questions, Dr. Boboyanov, would you like to respond to Dr. Tsui's comments briefly? Thank you.
Dr. Chi, thank you very much. Yeah, those are you have did a very good summary, and then also glad to have your suggestions, and I have to admit that there are a lot of interesting suggestions, and I need to I say we because not I directly, but with my student we can go one by on each of them, and then before I can reflect on them, I need to see like kind of implementability of them, but in overall all of them sound very interesting, and like kind of we have to put hands on, try and see if so are doable. I have only one question on related to the one of your comments. I mean, all of your suggestions are straightforward, and I understood all of them. I have only one question on the you have indicated, I think it's a third recommendation, to look at the slope instead of levels, and here I did not understand very much. Do you mean a trend? Do you mean to look at the trend, or how do you explain it? This I did not understand. The rest are of course very clear. This only I did not understand very much.
Yeah, maybe I can just briefly respond now. So in terms of that, I mean that you can compare. So for example, you can potentially have two subsamples. One is the subsample for places with high irrigation. The other is another subsample with low irrigation. And then you can run your regression on those two subsamples separately to see if your, say, temperature coefficients is going to be the same for two subsamples, or maybe the coefficients are actually different for the irrigated than the non-irrigated, so that you can infer how irrigation is going to buffer the potential effect of temperature. That's what I mean. Yeah.
You assume some kind of technological differences in the sample, like kind of you consider it as a different technology, like kind of not a homogeneous technology, but like kind of two different technology levels, some kind of in this direction.
Yeah.
Okay, yeah, we can have a look. It's I have to admit is only we can have a look is only I have to admit that you also say like 10 12 years data in district. Overall, we were very glad. I mean, we will have a look, and hopefully we will have something like significant. It's only there is only one challenge I have to admit is here. It was very difficult to get kind of the soil and irrigation water availability data at the district level, and therefore we end up some kind of relatively relatively short time horizon. I mean, if we had a wish, I mean, like kind of looking at climate change studies, I mean, the everyone of us here wishes to have 50-60 years of panel data with probably more than 300 observations, and I mean 300 districts or any units. But here we have to limit ourselves with 10-12 years, because that's the data we get. That's the main challenge we face. Usually not to include too many unlinear coefficients into the model. That's otherwise we could also have kind of like a translog function where we could have like kind of combination of many variables, but that was the main challenge, not to look at the translog function, but to limit ourselves and with more Cobb-Douglas, where we cannot directly include the combined effects. But again, thank you very much. But we will have a look. It's rather its data is very much limited. Also, we are very glad, but we also know the challenge associated with short time horizon, and but we will have a look, and yeah, as you indicated, maybe including some indices to capture the nonlinear effect or some threshold effect. Could have been a one effect, one possible solution, not to blow up the number of variables, but still to consider the nonlinear effect. Will have a look, and I would be glad if you could send us your suggestions via email. I tried to
Sure,
I
yeah,
made a
no
photo of your recommendations. I made a photo, but I need to look how the resolution of my photo is, but would be glad if you could send us your suggestions via email.
Okay,
Thank you
great.
very
Great to thank you to both of you gentlemen. Now, shall we open up the floor for Q&A? So as always, if you have any questions or comments to the presenters, please feel free to raise your hand by clicking the raising hand section at the bottom of the system. Okay. Now we do see a hand rising. Dr. Paria, do you have a question? Thank you.
Yeah, I have a question. So what I see, like the study has been done using the panel fixed effect model. Am I right?
Yes.
Yeah. Yeah. So the here I am seeing only the R square. Actually, in panel data analysis, we run three models parallelly, like pooled, random, and fixed effect model. So why your estimation is the optimal? Like no taste has been done, like for pooled and random effect LM test, and pooled and fixed effects there is a restricted depth test, and within random and fixed there is a Horstman test. So no results are there. So as I'm seeing that, I'm a little bit confused that this fixed effect model is appropriate for these estimations or not. Please go, if you have any results, you can reflect. And another things, like what you see in the Ministry of Irrigation, like I think slide number 8 or something, if showed a figure there, I saw some interesting data. Like here I see the Naib region and Tashkent region, the soil salinity is a little bit high, where in Tashkent region the soil salinity is low, but the productivity is low. But where in case of Naib, soil salinity is also high and productivity is also high. And in case of 3 or 4 districts, I am seeing this type of estimations, but your result is showing there is a positive negative correlations between it. And another thing is, like in your results, the result is showing that the groundwater salinity has a positive correlations with the productivities. So can you explain a little bit more, like why this result is showing and what is the mean of it? Thank you.
Okay, thank you. Dr. Babayarov, do you mind responding just very briefly within 1 minute? Thank you, sir.
How many sentences you allow me to answer for each question?
Okay.
Tell me, I answer only with the limit of the sentences. Yeah, can I say only one sentence for each of the
okay.
answers?
Go ahead, please, sir.
The question number 1, the different models. The keyword is a Hausmann test. The Hausmann test says that we can use fixed effect model, and then when we have a fixed effect model, then that doesn't make to bother so many people here with other results, when then fixed effect model is the most suitable. And then second one on the visualization of the figure on the soil salinity and the yield. This was for demonstration purposes and not to try to correlate the estimate the correlation there, because this is a regional level data I presented on this level is a regional data and not district level data. Even you have this is a regional averages. Even you have a regions, you might have inside the region various districts, and then districts may have a different level of soil salinity, and therefore it's rather not to estimate the correlation at the regional level when we have a disaggregated level, and therefore at the disaggregated level you can see the results that when you do analysis at the disaggregated level, that it shows that it has a negative effect and not a positive as you assume. And related on the issue of the groundwater salinity, this question we also expect to come also from the review process. It's mainly associated that the groundwater salinity is important, but it does not reach the rooting depths of the wheat, and therefore the wheat is like, I don't know, I'm not an agronomist, but should not go more than I think the rooting depth should not go more than half meter or 1 meter probably. I keep some buffer and say 1 meter, and when someone comes and shows me a picture that it goes more than 1 meter, but I think it should not go on 1 meter. And then groundwater is there, especially in winter and autumn seasons, it's below 5 or 6 meters, and therefore it should not be a main parameter to influence on the crop productivity. But why we included it, but we still included it there is to avoid unobservable variable, because
sorry to interrupt, Dr.
Okay.
Babayanov. May I
Okay.
suggest that we continue the discussion after the presentation or in the chat box, because we have to move on to the next presentation. Thank you very much. Now, with that, let's move on to the last but not the least presentation of this afternoon. The presentation is on weather shocks, irrigation development, and multi-dimensional poverty. Evidence from panel data in emerging economies of Thailand and Vietnam. I was just informed by the organizer that there's a little bit update about the schedule. So the presentation will be delivered by Dr. Meng Hong Do, a PhD candidate from the Institute for Environmental Economics and World Trade, Leibniz University, Hanover, Germany. So the floor is yours, Dr. Do. Thank you. You have up to 15 minutes.
Thank you, Professor Liu. And could you see my slide and hear me clearly?
Both clearly. You're good.
Okay, great. Good afternoon, everybody. My name is Meng Hong Do. I'm a PhD student from Leibniz University, Hanover in Germany. First of all, I would like to express my sincere thanks to ADBI for organizing this significant conference. Now I will present our studies on weather shock, irrigation development, and multidimensional poverty with evidence from panel data in 2 emerging economies, Thailand and Vietnam. Right. Let's about the content. My presentation includes 6 sections. I will first talk about the motivation of our study, followed by the literature review and our contributions. Next, I will talk about the research data and methods. Then I will present some key findings, and finally the conclusion and some policy indication. Let's start with the motivation. Water is essential for life and underpins socioeconomic development. Managing water resources is becoming more critical in emerging economies in Asia, such as Thailand and Vietnam. These countries have a rapid economic development and population growth. A large share of the population still relying on agriculture, but they also have to face with a changing climate. It's widely known that water is becoming scarcer, and thus using water more efficiently is essentially needed. However, addressing this challenge is even more difficult in the context of climate change. Extreme weather events such as droughts and floods seem to be more frequent and severe due to climate change. As agriculture is a weather-sensitive sector, these events not only pose a threat to sustainable water management, but also to the global food security. So in this regard, irrigation development may be a solution to improve sustainable water management and at the same time improve agricultural production. The previous studies have shown that access to irrigation has a significant influence on improving agricultural productivity and crop income, ensuring food security and providing employment opportunities and reducing poverty. This is the reason why investing in irrigation is important and has been a priority of many governments in the global south. However, the focus of this investment is mainly on making access to water for irrigation is available to farmers. And furthermore, some other studies found that the effects of irrigation on poverty could also be insignificant or negative. We found several research gaps that are worthy of attention. Firstly, climate-driven changes in precipitation and drought patterns have caused water scarcity. Furthermore, the demand for higher agricultural productivity results in an increasing demand for water and an increasing conflict amongst water users. This implies that the investment to just provide access to irrigation may not be sufficient, but ensuring the availability of irrigation water throughout the year may be more useful. However, evidence on the role of year-round irrigation in coping with the extreme weather events is rare. Secondly, studies on the impact of irrigation have paid more attention to partial productivity measures, for example, crop output or revenue per hectare, while evidence on the effects of irrigation on farming efficiency is much less studied. Thirdly, the evidence on the effect of irrigation on poverty appears to be mixed, or most of these studies relied on a fixed threshold of income to measure poverty. This measure of income-based poverty has many disadvantages. So we enrich the literature with evidence on the influence of irrigation on multidimensional poverty. And lastly, some of the previous studies on the impact of irrigation employed cross-sectional data and did not address the problems of unabsorbed heterogeneity and endogeneity. So the use of cross-sectional data may not well reflect the impact of irrigation, because the investment in irrigation are long-term and the adoption of irrigation at household level is endogenous. So we contribute to the literature by addressing these problems. We aim to fill the above research gaps by identifying the role of year-round irrigation in helping rural households to cope with weather shocks, and examining the effects of irrigation on farming efficiency, and evaluating the impacts of irrigation on household income and poverty. We believe that the findings from our study are important to stimulate policy and investment with regard to the development of irrigation and water management at local levels. The main data in our studies come from the Thailand-Vietnam socioeconomic panel, and in each country, the TVSEP data comprise the information of about 2,200 households from 220 villages in 3 provinces. They are Nakhon Phanom, Buriram, and Ubon Ratchathani in Thailand, and Hà Tĩnh, Thừa Thiên Huế, and Đắk Lắk in Vietnam. In this study, we used a balanced panel data of 3,380 households from Thailand and Vietnam in 3 grades of 2010, 2013, and 2016. The final sample includes 10,140 observations from the 2 countries. Besides the TVSEP data, we also employed the precipitation data from the tropical rainfall measuring distance to instrument our endogenous variables. And it's important to note that these rainfall data are only available for the year between 1998 to 2014. Moving to the data description, panel A of the table show that rural households in Vietnam have a higher share of irrigated land areas, more than 70% compared with Thailand. And in 2010, 28% of households in Thailand and 40% households in Vietnam reported that they experienced a weather shock. This figure show an increasing trend in Thailand, where it's rose to 33% in 2016. And in the case of Vietnam, the exposure to weather shocks dropped to 18% in 2013, but it's increased again to 23% in 2016. Panel B presents key variables of village irrigation. The improvement of year-round irrigation is observed in Thailand when the availability of year-round irrigation increased from 32% in 2010 to more than 60% in 2016. On the other hand, this variable in Vietnamese villages was about 60% between 2010 and 2016. We also control for other variables at household and village level. However, due to time limits, I would not show the descriptive of these variables. So we use two different approaches to measure poverty, namely the absolute poverty and multidimensional poverty. In the case of absolute poverty, we use the World Bank poverty threshold for middle-income countries at a daily income per capita of 3.2 PPP dollar. Regarding the multidimensional poverty, we adopted the multidimensional poverty measure from the World Bank and included 4 dimensions of household characteristics, namely monetary measure, education measure, access to basic infrastructure, and housing and living conditions. We set the cutoff level at 0.25 or 1/4. In other words, a household is classified as living in multidimensional poverty if this household has the total number of parameters adding up to 0.25 or higher. So moving to the description of household income and poverty, panel A of the table on this slide show that Thai households have significantly higher daily crop income and daily total income per capita compared to Vietnamese households, and both show an increasing trend. From panel B, we can see that Vietnamese households are more likely to have unsafe drinking water, no improved sanitation, having malnourished child, and having inadequate housing conditions. On the other hand, Thai households are more likely to have no primary education of adult members. In panel C of this table, we can see that Vietnamese households appear to have higher incidence of living in poverty in both absolute and multidimensional poverty. Now, we'll talk about the method. In the first step, we examine the role of year-round irrigation in defining the irrigation of rural households. We employ a fixed effects estimation model to account for unobserved characteristics of households, and as shown in equation 1. The dependent variables in equation 1 is the IIT, is the share of irrigated land areas of household I at time t. And in addition to the estimation of equation 1, we also examine the coping against shock role of year-round irrigation by including an interaction term between the shock exposure, the XIT here, and the availability of year-round irrigation at village level, the YIJT in this equation. In our study, we cluster on estimation at village level to have robust standard errors and to prevent for autocorrelation. In the next step, we investigate the effects of irrigation on farming efficiency. We employ the time variant stochastic frontier model with the true random effects specification suggested by Greener, and the correlated random effects model suggested by Moonlab to address the potential problems of endogeneity caused by omitted variable as shown in equation 2. The farming efficiency is then predicted as specified in equation 3. Next, the predicted farming efficiency scores from equation 3 will be included as the dependent variable of fixed effects model to examine the impacts of irrigation on farming efficiency, as you can see on in equation 4. There are two concerns regarding the irrigation variable, the IIT in equation 4. First, we could not justify if the reported share of irrigated land areas is before or after the crop production season. So to account for this issue, we included an additional estimation with a dummy variable of improved share of irrigated land areas from the previous period. This dummy variable helped us to clarify if an improved irrigation from the previous years can have an impact on this year farming efficiency. And secondly, the share of irrigated land areas appears to be endogenous in equation 4. So we address this problem by using the fixed effect estimation with instrumental variable for panel data. We construct an IV relied on the tropical rainfall measuring missions precipitation data by calculating the standardized rainfall anomaly index for each village in each year. Since the data set is available for the period between 1998 to 2014, we use the last 3 years standardized rainfall anomaly index as the IV for the irrigation variables. In the last step, we examine the impacts of irrigation on income and poverty of rural households. In this case, the model of fixed effects estimation with IV is applied as in equation 5. The dependent variables, the YIT here, can be crop income per capita, the total income per capita, income poverty at 3.2 PPP dollar per capita per day, and the multi-dimensional poverty. Here we use the last 3 years share of irrigated land areas to reflect the irrigation at household level, and to instrument this irrigation variable, we use the same IVs as mentioned in the previous section. So now we move to the result. This table shows the factor affecting the share of irrigated land of rural household. As expected, the exposure to weather shocks have a negative and significant association with household's share of irrigated land areas. Furthermore, the coefficients of the interaction between weather shock and year-round irrigation is positive and significant, implying the important role of providing year-round irrigation in the context of weather shocks. In addition, year-round irrigation with reservoirs as the major source of irrigations play a more important role in increasing the share of irrigated land areas of rural households. On the other hand, year-round irrigation with dams as the major source of irrigation does not have any significant association with the share of irrigated land areas. Since we don't have much time, I will skip the result of farming efficiency estimation. This table presents the result of the effects of irrigation on farming efficiency of rural household. Regarding the weather shocks, the results show that weather shocks negatively affect farming efficiency in Thailand and Vietnam, and the share of irrigated land areas have a positive and significant influence on farming efficiency. This is also true for the variable of improved irrigated land areas in the current period. Our results provide evidence that the better irrigation helps increase farming efficiency in the context of weather shocks. On this slide, we show the impacts of irrigation on household income and poverty. The result depicts some important findings. First, the exposure to weather shock negatively and significantly affect household crop income. The last share of irrigated land areas had positive and significant impact on daily crop income and daily total income per capita. Lastly, we further find that the large share of irrigated land areas of rural households has negative and significant influence on absolute poverty and multidimensional poverty. So our study pointed out some important findings. Firstly, the availability of year-round irrigation at village level positively and significantly helps to increase the share of irrigated land areas and reduce the effects of weather shock on irrigated land share. Year-round irrigation with reservoirs as the major source of irrigation at village level plays more important role than year-round irrigation with dams. Secondly, weather shocks significantly cause a reduction in farming efficiency, while the share of irrigated land areas has a positive effect on farming efficiency. An improvement in irrigated land share of the previous period also has a positive effect. This indicates that better irrigation has increased farming efficiency. Lastly, the last values of irrigated land share has positive effect on crop income and total household income and contribute to the decrease of income and multidimensional poverty. These findings have important policy implications with regard to irrigation development for fighting against increasing weather shocks and poverty. Firstly, policymakers in developing countries and international donors should pay more attention to irrigation development and water management to ensure year-round irrigation in rural areas. In the context of climate change, having access to irrigation is not sufficient for farmers, but year-round irrigation. The development of water reservoirs may be more efficient in improving irrigation at household level. We recommend that the irrigation development projects should focus on reservoirs instead of dams, and further consider combining them with more efficient irrigation technology at farm levels to ensure the availability of water. Lastly, the development of irrigation should also come with infrastructure development and transportation. For example, information and communication technology, along with a better irrigation, improve rural roads, and ICT can significantly increase rural household income and reduce poverty. The availability of ICT may further stimulate the application of technology for more efficient irrigation. And that's all from me. Thank you for your attention.
Thank you very much, Dr. Dong. That's very interesting. Now, let's invite the discussant for this presentation, Dr. Chen Ji, an associate professor from the Department of Agricultural Economics and Management, Zhejiang University, People's Republic of China. Dr. Ji, the floor is yours. You have up to 10 minutes. Thank you.
Hey, thank you. Thank you, Professor Liu. Long time no see. Okay, so can you see my slides clearly?
Yes, very clear. Go ahead.
Okay, thank you. Hey, thank you, Dr. Du. Thank you for a nice presentation. And also thank you, ADBI organization for inviting me again to serve as a discussant to give some comments to this nice paper in this conference. And so I'm Ji Chen from Zhejiang University, and the paper's title is Weather Shocks, Irrigation, Development, and Multidimensional Poverty, Evidence from Panel Data in Emerging Economics of Thailand and Vietnam. And so I think, and generally, the paper is clearly written, and I see the authors have done substantial work. And the paper is very well structured, and the paper also provides lots of insightful results. So I might skip this summary of the paper, but go directly to some comments that I would like to give the authors. So I will go one by one. So in the first table, in table 1, I read the paper according to the statistics here. It seems that no matter for Thailand or for Vietnam, there should be some villages with year-round irrigation, but they do not rely either on a reservoir or a dam as the major irrigation source. As you can see the data here. I raise this point because you offer the final implication saying that it's better to build more reservoirs instead of dams to cope with extreme weather shocks. So it seems that there are other options for the farmers or for the households to cope with the weather risks apart from reservoirs and dams. So maybe you can provide us some information on this point. Maybe they rely on some other sources to irrigate. And in table 4, regarding the factors affecting the share of irrigated land areas, you use this fixed effects estimation. I think I have 5 comments here on this table. The first is, I think there might be some other factors that could influence the household irrigated land areas, such like the distance and comparative slope, the location between the household farm and the reservoir or the dam, as well like factors of soil quality of the household farms, the irrigation costs of the farms. I think if you have the data, these variables also need to be included. Otherwise, you will meet some omitted variable bias in the estimation. And secondly, I think the study explains the significance of the association between year-round irrigation and the share of irrigated land areas, but you miss the explanation of the magnitudes. So maybe it's better you, apart from explaining the significance of the relationships between the variables, can also provide some explanations on the magnitudes. And third is, it seems that it's the role of year-round irrigation with reservoir or year-round irrigation with dam, their influence on the share of irrigated land areas under weather shocks, as you can see here, the interaction terms between weather shocks and year-round irrigation, and weather shocks interact with year-round with reservoir. It seems that the influence are not significant. So we might want to explain why under the weather shocks, the roles of year-round irrigation with the reservoir and year-round irrigation with dam on the household irrigated land areas are not significant. And the fourth comment is that you mentioned that the result from this table seems valid because many dams in Vietnam have a low value of irrigation per cubic meter, and reservoirs play an important role in supplying water for agricultural production. So could you please provide us some background information on why the dams have a low value of irrigation per cubic meter, while the reservoirs play more important roles? Whereas I myself am not an expert in water resource management, so I think I'm curious, and maybe as a reader, they will be interested in knowing some background information on this point. And the last comment on this table is that the year-round irrigation at village level actually is endogenous. So do you have any possible solution for solving this endogeneity problem on this year-round irrigation variable? And my next comment is regarding the equation 6 and table 7. They are actually related. So you mentioned that you used the lagged 3-year SRAI as an IV for the irrigation variable. But intuitively, the lagged 3-year SRAI would have both influence on dependent and independent variables. So how would you justify that the reasons that you use this variable as an IV? So maybe you can refer to some other articles which use the falsification tests of the IV that you chose. And the second comment is that maybe you also want to add some explanations on the magnitudes of the farm efficiency effects of the irrigation here. Next,
excuse me, Dr. Ji. Can you quickly wrap up in about 1 minute?
Okay.
Thank you.
Okay. I will go quickly. So next comment is kind of similar with table 7, some more falsification test of the IV. And maybe we want to also provide some explanation of the economic meanings of this magnitude, the irrigated land area on the influence of reducing multidimensional poverty. And some other comments. Well, I may skip here to some last comments. I think maybe besides using fixed effect model and IV method, as you have the panel data here, maybe you can use some other methodologies like PSM, DID, to provide some robust tests. And you may also want to do some heterogeneous effects to provide more evidences, like for different types of weather shocks and for some different places, more vulnerable places and less vulnerable places. And I think it also be important to be a little more cautious to give the policy implication to suggest to provide more reservoirs instead of dams, considering that they both could have some spillover effects or externalities, the positive externalities or negative externalities. So maybe it's not only socioeconomic problem, but also related to some other considerations like producing electricity, the ecological values as well. And some other very minor comments that you may want to skip. You may want to delete this sentence in your abstract, because I think internet is not a focus of your research objective. Sorry. And it'll also be good if you can provide some more explanations on why technically dams are not good irrigation tools as coping strategy to weather shocks. Okay, thank you for your attention.
Thank you very much, Dr. Ji, for your great comments. And I know we are behind the schedule, but I still want to take a couple of questions for Dr. Daw. So I do see two hands rising. Who goes first? May I suggest that Dr. Ajo go first, please? Thank you.
Thank you very much. It was a very excellent paper. Yeah, I really appreciate the efforts done by the authors. My simple queries are, how do we, integrate conceptually about these multidimensional poverty aspects in the paper? That was really, crucial issue, and it has multiple dimensions. It has also the aspects of livelihoods and other options. So it's a bit bigger one. So it's a challenging issue even for them. So it would be better that if they provide some of the conceptual framework just to link those issues in the context. That would be very good for the general readers of the paper. That is what my general comments. For other estimation issues, there are several things which has been mentioned by Dr. Chenji, and I appreciate those comments and elaborative issues on that one. So these are the things I really want to bring those issues in the context, and also to see how it has the impacts on overlinkage of water scarcity, irrigation issues, weather shocks, and the overall framework. How does it create the impacts on multidimensional poverty or the food security, what we are looking for in the special issue? And that was the major concern, when we initially started the special issue between me and the other co-editors. Yeah, thank you very much. Yeah.
Okay, thank you very much, Dr. Ajo. Now, shall we invite Dr. Perio? Dr. Perio, do you have any quick questions or comments? Thank you.
Yeah, I have questions on the one dimension, what the author is using, the monetary dimension for poverty estimation. You mentioned that the per capita poverty line actually $3.20. It's stated by World Bank, but you are taking from 2010 to 2018 data. So the inflation is there. So if you calculate based on that, then there will be an error in between, and you are putting a binary number that these households are poor and non-poor, and based on that your multidimensional poverty you are estimating. but you are not mentioning. Have you mentioned the inflation section? Like, have you deflate the inflation?
Yeah, we did. All the PVP dollar, the monetary value in our study are based on the 2005 constant price, based on that, inflation free.
Okay. But in every period, 2010 to 2018, each and every period, the monetary slabs for poverty line are different. Over the year, it's improving based on the dimension they are taking. So if you take care of that when you are calculating the monetary dimension. And second thing is like, my second question is based on the data. Like you are considering 2010, 2013, and 2018 data for, I think, 1,699 households. Am I right? So, yeah.
Yeah, no, we take 2010, 2013, and 2016, and the total households numbers is 3,380 households in Thailand and Vietnam.
So all the households are being repeatedly sampled, or these are the aggregated result?
Yeah, as I mentioned, in each year, the TVSAP data comprise the information of 2,200. So we take only identical households. Those only appear in the panel. So that's why the reduced number from 2,200 to 1,600 something in each country.
Okay. And the last question is based on model selection. What I previously asked, why fixed effect model? Like, why not random or why not pooled? No taste are there. So thank you.
Okay, thank you very much, Dr. Leo, for those questions. Sorry, Dr. Do. Do you mind quickly respond just within 60 seconds to the comments?
Okay. I will speak really fast.
And other participants, thank you.
Yeah. First of all, I would like to thank Professor Yi for your comments, and I could see a lot of them is really constructive and useful, relevant for us to improve the paper. We will consider and incorporate that. And also from Professor Araya, your recommendation also, we will take into account that too. Yeah, it's really useful for us. And finally, to Paria, in any case, the panel estimation, the fixed effects always yield the best result. For example, the Hausmann test is only test if the random effect is consistent as the fixed effect model. So in any case, fixed effect is better. Just if the real model is random effects, we will need the test to prove that. And in other case, fixed effect is still the way to go. Thank you.
Okay, with that, thank you very much to Dr. Do and also Dr. Ji and the participants. Sorry, I had to rush you through this because we do want to get the journal overview for the special issue. But before I hand over the mic back to Dr. Dio, I want to take a couple of minutes. I just want to express my gratitude to ADBI for inviting me to serve as the chair of today's session. To me, it's quite an enjoyable and a learning experience. So I really enjoyed a lot and learned a lot from all the presenters and the discussants and the participants. And I feel always delighted to meet older friends and make new friends during this conference. And I was even grateful to see that so many brilliant scholars, and most of them are quite young, PhD candidates or fresh out of graduate school. They have conducted excellent work on such an interesting topic. So water, irrigation, poverty, productivity, and the list go on and on. I really want to thank ADBI because water is always an important topic, and it deserves further and more research and in order to inform the policy. I think this topic is not only relevant to areas covered in the presentations, but also to Asia and to the world as a whole. So thank you, ADBI, for organizing such a conference. And last but not the least, I want to take this opportunity to thank you again to all the excellent presenters, discussants, and the participants. And last but not the least, once again, many thanks go to ADBI, to the Dean, to Dr. Deal, to the entire team. So thank you all very much, Dr. Deal. So back to you. Thank you all. Thank you. Hopefully we can see each other in person in the near future somewhere. Okay.
Thank you. Thank you so much. Thank you so much, Professor Chang Feng. We really appreciate your time and also your remarks. So, but before we close, I would like to request, we have actually Professor Cecilia for the closing remarks. Professor Cecilia is the editor-in-chief for this International Journal for Water Resource and Development. Professor Cecilia is actually currently professor in practice on environmental innovations, Schools of Interdisciplinary Studies, University of Glasgow, UK. And she's also adjunct senior research fellow at Institute on Environment and Sustainability at Likwano Schools. She has over 30 years of experience in water, environment, and natural resource management in the context of development. She's working at present on impact of global changes on water resources, food, environment, and society. She's the winner of Crystal Drop Award in 2016 and the 50th Anniversary Award in 2021. International Water Resource Association, a member of, she's also a member of International Selection Committee, Millennium Technology Prize, Technology Academy Finland, and there she has so many credentials. In fact, she's an authority in water research. She and her husband, actually her husband, Dr. Biswas, was also the winner of the Stockholm Water Prize. They are very fascinating researchers, has done lots of work and has made significant contributions. But then she really wanted to come, present in person and make these presentations. But then unfortunately, she is currently taking a flight from UK to India, so she couldn't do it in person. And her presentation is recorded, and we'd like to play the presentations. Dr. Panaroth, would you like to start the presentation of Professor Cecilia?
Good afternoon. I would first like to thank Dr. Dilra Hood, Vice Chair of Research and Senior Research Fellow at the Asian Development Bank Institute, for inviting me to give the closing remarks today for this very timely conference on water resource management in agriculture for achieving food and water security under climate change in Asia. We know that agricultural irrigation accounts for 70% of water use worldwide, over 40% in many OECD countries. In 2018, this amount was calculated to be 820 cubic kilometers per year based on aggregated country-level reports from the same year. It is estimated that by 2050, the global water demand for agriculture will increase by a further 20% due to irrigation needs. With climate change and with an increasing number of users and uses that compete for the same water resources, our concern is whether this amount of water will be available. Studies reveal large impacts of global food demands on global freshwater resources. As agriculture becomes more water intensive, more water is embedded in its produce, with growing international imports and exports, representing the so-called trade in this virtual water. While it is argued that this contributes indirectly towards food security, it directly affects quantity and quality of water in food-producing arid and semi-arid regions. For these regions, it is said that it would be more sustainable to import agricultural products and the associated virtual water from regions that are not water scarce. It is also said that this would reduce and perhaps even avoid freshwater depletion and pollution in countries of destination. What it is not said, however, is that this would not help countries of origin. In addition, with climate change and changing precipitation patterns, it may be that water-abundant basins and countries will become water scarce. Thus, the increasing frequency and duration of droughts makes it essential for public and private institutions and users alike to understand and improve management practices. That is where the change is going to come. In the case of groundwater, despite depletion and pollution, its use for irrigation has benefited local and national economies, both in the global South and global North. For governments in OECD and non-OECD countries, it would be almost impossible to withdraw agricultural subsidies that support irrigation and that are estimated at $70 billion per year, 536 billion of them that are directly paid to producers. This even when eliminating minimum prices of subsidies in arid or semi-arid countries for crops that are water intensive would greatly contribute to better management of water resources. Overall, we see a world with a growing gap between demand for and availability of water at local levels, and with intensive agricultural practices contributing to the severe degradation of the environment, and which in turn can threaten both livelihoods and freshwater ecosystems in basins and countries of origin. Scholars suggest that to adapt to climate change, regions and countries should grow less water-intensive crops. They also suggest that irrigated agriculture should be converted to rain-fed agriculture, even for valuable crops. Being realistic, however, neither of these changes is likely to be attractive to farmers compared to the reliability that irrigation provides. Therefore, management is important. Urgently needed are governance mechanisms with joint management of resources and appropriate forms of shared decision-making by actors at the national and local levels, and also goals that are broadly agreed and locally implemented, features that are lacking at present. Now, in this very timely special issue that will be published in the International Journal of Water Resources Development, and which papers I'm showing in these slides, many of these topics will be discussed. The International Journal of Water Resources Development, of which I am the editor-in-chief, is a policy and practice-oriented journal. Our mission is to improve the access and use of water globally, by publishing the latest developments in planning, policymaking, and management from all over the world. Our journal is read by academia, industry, policymakers, and legal teams globally because of the high-quality papers published that can contribute to solving real-world water problems. This is also what we know will happen with this special issue, that it will contribute to solve real water problems. At the journal, we will be very pleased to publish this special issue on water resource management in agriculture for achieving food and water security under climate change in Asia. As we know, it will contribute to improve the knowledge in the area. Thank you.
Thank you. Thank you very much. This was a very wonderful presentation, although it was video recorded, but it had great insight. And being an authority in water issues, we were delighted to have her presentations and listen to her. So before, I think, we had a very interesting discussions, interesting presentations throughout 2 days. And most of the presentations were of very high quality. Every one of you have put in lots of effort to bring in very high quality paper. And also the discussions, I'd like to thank all the discussions. You have really taken time to read the paper, made a very careful comments, and I'm sure it will be a big contributions to the authors, and they will be able to take into account the comments provided by the discussions and other participants. So that was very, very useful, and I really appreciate and congratulate all of you. Now, I would also like to reiterate what Professor Chang Feng has said, that most of the scholars who presented were very young scholar, very recent PhD student, or some of them who are still PhD student. That itself shows the commitment of all the young researcher and academicians to bring about a change, particularly in water resource management. As you know, water is an intergenerational issue. It's not about increasing only the productivity. It's also about sustainability. It's about how we manage water resources so that we leave something behind for our next generation to come. So that's something that we have seen in today's presentations, as well as in some of yesterday's presentations. And I would like to, as a guest editor, I think we all would like to see that the policy aspect is brought out very strongly in the paper, and also the issue of sustainability is very strongly spelled out. So that's something that we'd like to see. But on the whole, I think we are very satisfied. We are very delighted with the contributions. But before I conclude, I would like to thank Dean Sonobe, who is also a guest editor, and for his opening remarks. It was very nice. And then we had Theo Ankev, who provided a keynote speech, and his keynote speech had lots of information. It was loaded with valuable informations. Then we'd also like to thank all the chairs. We had Thomas Panella from ADBI, we had Netra, and then Professor Chang Fan Liu, who also made time to be with us. So I'd like to thank all the chairs. Thank you so much. And I'd like to thank Dr. Ariel, who is also a guest editor here. I'd also like to thank Wang Lingma for his very, very always being supportive to us and helping us find reviewers, helping us find many other important persons. So yeah, thank you so much. And I shouldn't forget to thank few people who we don't see, but they are the pillar behind making this happen. One is I think Dr. Panaroth. She has been working tirelessly, and thank you so much, Dr. Panaroth. And I would also like to thank Dr. Raja. He has been also working very tirelessly for us to be, to allow us to come here and present. And my friend Mami-san, Mami Nemoto-san, and Mami Yosoda-san, they have been working very tirelessly to make this happen. So thank you so much. And once again, I'd like to thank all of you from the bottom of my heart. ADB, I would like to express lots of thanks and gratitude, and I hope you'll continue to do this interesting research and really make a genuine difference on the future of this planet. Thank you so much, and I would like to give a big hand to everyone. Thank you very much. I hope we will meet in person, with COVID ending, and we'll be able to have a wonderful conference devoted on water. And thank you everyone for taking time and your presentations and your discussions. I really, really appreciate. Thank you very much from the bottom of my heart.
Thank you.
Thank you. Thank you. Bye.
Thank you, Dio. Bye-bye.
Bye. Thank you. Thank you so much.